The most famous photograph ever taken of space might be showing us something that no longer exists. Right now, as you listen to this, the pillars of creation could be nothing more than a memory, an image of structures that were torn apart and scattered into dust 1,000 years ago. We just haven't seen it happen yet. The light showing their destruction is still traveling toward us through the vast darkness of space, and we won't know until it arrives, perhaps in another 1,000 years, whether the pillars we see tonight are real or ghosts. But here's what makes this even stranger. Even if they're already gone, even if we're watching an elaborate cosmic recording of something that was destroyed while Charlemagne ruled Europe, what we're witnessing is still one of the most profound processes in the universe. Because inside those pillars, whether they still exist or not, we're watching stars being born. We're seeing the universe create new suns, new solar systems, new worlds. And in October 2022, we saw something nobody expected. We saw inside them, the pillars of creation. You've seen the image, even if you don't know its name. 3 towering columns of cosmic gas and dust, rising like mountains against a glowing background, dark and imposing and ancient-looking. When the Hubble Space Telescope captured them in 1995, the photograph became instantly iconic, perhaps the most recognizable astronomical image in history. It appeared on everything: museum walls, coffee mugs, dorm room posters, postage stamps. It was beautiful, yes, mysterious and profound. But it was also hiding something. What Hubble showed us was a lie, not an intentional one. Hubble's cameras captured what they could see: the surface of these structures, their glowing edges, their dark cores. It looked solid, impenetrable, like stone monuments carved by cosmic forces. But it wasn't stone. It wasn't even solid. Those dark pillars were almost entirely empty space. Diffuse gas so thin that the densest parts would still be considered a near-perfect vacuum by Earth standards. And hidden within that darkness, concealed behind curtains of dust that visible light couldn't penetrate, hundreds of stars were being born, glowing in wavelengths our eyes will never see. Then, James Webb looked at the same pillars, and the universe transformed. Where Hubble saw darkness, Webb revealed light. Where visible wavelengths showed impenetrable walls, infrared vision unveiled translucent veils, glowing with the heat of stellar birth. The pillars that looked like solid monuments became semi-transparent structures filled with dozens of glowing red orbs, protostars, infant suns, each one marking the place where gravity is pulling matter together into something that will eventually shine for millions or billions of years. For 27 years, we thought we understood the pillars of creation. Webb showed us we'd barely scratched the surface. This is not a story about one telescope replacing another. It's a story about sight itself, about how what we see depends entirely on how we look. It's about 2 different ways of observing the same cosmic landscape and discovering that each reveals a completely different truth. And it's about the most fundamental question in astronomy. Not just what's out there, but how we can possibly know what's real when we're looking at light that left its source before recorded history began. Hello there, and welcome to the Sleepy Science Channel. I'm so glad you found your way here. Perhaps you've had a long day and need something to help you unwind. Or maybe you're the kind of person who finds peace in cosmic mysteries, those deep questions that seem to matter most when the world grows quiet and still. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your shoulders drop, your breathing slow, and your thoughts drift like clouds across a twilight sky. Because tonight, we're traveling somewhere extraordinary. We're going to one of the most photographed, most beloved, most mysterious places in the entire universe. We're going to understand not just what the pillars of creation are, but how 2 very different telescopes, separated by decades and technology and 1 million miles of space, saw two completely different versions of the same cosmic truth. We'll explore the moment in 1995 when Hubble first captured these towers of creation and changed how humanity saw the universe. We'll discover what visible light can show us and what it conceals. Then we'll journey to James Webb, orbiting the Sun almost 1 million miles from Earth, operating at temperatures so cold that nitrogen would freeze solid, revealing the cosmos in wavelengths our eyes will never perceive. We'll witness how infrared vision transformed our understanding, exposing hundreds of stars that Hubble couldn't detect, showing us stellar birth in unprecedented detail. And along the way, we'll uncover some surprising truths. We'll discover why these solid pillars are actually more empty than solid. We'll learn that the beautiful, pristine structures we admire are actually being destroyed even as we watch them. We'll find out that the stars being born inside them might have their growth violently cut short. And we'll understand why we need both perspectives, both telescopes, both ways of seeing, to even begin to comprehend what we're witnessing. Some of what you hear tonight might surprise you. Other parts might simply wash over you like a gentle tide, soothing and curious, and quietly unforgettable. This is the story of two telescopes, two visions, and one extraordinary region of space where the universe is actively creating new suns, building new worlds, writing new chapters in the eternal story of cosmic evolution. And just before we begin, if these calm explorations through science and wonder help you unwind, or give you something fascinating to ponder as you drift toward sleep, consider liking and subscribing to the channel. It helps others find their way here too, one curious mind at a time. Now, let's begin. Let's journey to the Eagle Nebula, to those towering pillars of gas and dust, and discover what it truly means to see the universe through different eyes. The birth of an icon, Hubble's 1995 discovery. It was April 1st, 1995, April Fool's Day. And when Jeff Hester and Paul Scowen of Arizona State University saw the first processed images from the Hubble Space Telescope, they must have wondered for a moment if the universe was playing a cosmic joke on them. They weren't expecting what they saw. They'd planned this observation carefully, targeting a specific region of the Eagle Nebula that ground-based telescopes had glimpsed but never captured with real clarity. They knew there were structures there, dense columns of gas protruding from a molecular cloud. But what emerged from Hubble's data was something else entirely. Not just columns, but monuments. Not just structures, but architecture that looked like it had been designed by forces beyond imagination. Here's what makes this even more remarkable. They almost chose a different target entirely. The Eagle Nebula was on a list of potential observations, but so were dozens of other star-forming regions. If the observation committee had prioritized differently, if the scheduling had fallen another way, the most iconic astronomical photograph in history might never have been taken. The universe's timing, it seems, is everything. And there's another secret. What we call the pillars of creation was almost called something else entirely. The name wasn't official NASA terminology. It came from the title Hester and his team chose when presenting the image. They borrowed the phrase from a sermon by Charles Haddon Spurgeon, a 19th century London pastor who spoke of the pillars of creation as the foundations of existence itself. The name resonated. It spoke to something deeper than science alone could capture. It acknowledged that what we were seeing was not just astronomical data, but something approaching the sacred, a glimpse into the very process by which the universe builds itself. The imaging process was meticulous and complex. Hubble's Wide Field and Planetary Camera 2, installed during the first servicing mission just 2 years earlier, captured 32 separate images using 4 different CCD sensors. Each sensor looked through different filters, isolating specific wavelengths of light emitted by particular elements in the cloud. One filter captured the glow of hydrogen atoms. Another isolated singly ionized sulfur. A third detected doubly ionized oxygen. Each filter revealed a different layer of the nebula's structure, a different aspect of its composition and temperature. When these 32 grayscale images were combined, with colors assigned to represent different elements, the result was breathtaking in ways nobody anticipated. 3 massive columns of gas and dust rose from the bottom of the frame, their edges illuminated with golden and rust-colored light, their dark silhouettes seeming almost solid against a background of glowing emerald and amber nebulosity. They looked less like gas clouds and more like monumental architecture, like pillars holding up the ceiling of some vast cosmic cathedral, or rock formations sculpted by ancient forces into shapes that shouldn't be possible. But here's the twist that nobody understood in 1995. What looked so solid, so permanent, so monument-like, was almost entirely empty space. The dense regions of these pillars contained perhaps a few thousand molecules per cubic centimeter. That sounds like a lot until you realize that the air you're breathing right now contains about 25 billion trillion molecules per cubic centimeter. The densest parts of the pillars of creation are a near-perfect vacuum by Earth standards, more empty than the best vacuum chambers we can create in laboratories. And yet, despite being almost entirely nothing, these structures were massive enough, dense enough, concentrated enough that gravity was winning. Inside those wispy clouds that looked like solid stone, matter was collapsing, pulling itself together, slowly transforming from diffuse gas into concentrated cores that would become stars. It's one of the universe's most elegant paradoxes. The densest stellar nurseries are emptier than anything we encounter on Earth, and yet they're substantial enough to birth suns. The tallest of the 3 pillars stretched roughly 4 light years from base to tip. To put that in perspective, 4 light years is nearly the distance from our Sun to Proxima Centauri, the nearest star to our solar system. This single column of gas and dust, one pillar among 3, spanned a distance so vast that light traveling at 186,282 miles per second would take 4 years to traverse it. And yet, from 6,500 light years away, Hubble captured it in exquisite detail. But the true revelation wasn't just in the pillars' size or their dramatic appearance. It was in the details that emerged when astronomers looked closely at the image. Along the edges of the columns, particularly at their tips, they found something extraordinary. Small, finger-like protrusions extending from the main structures, each one capped with what appeared to be a dense knot of material. These knots, each larger than our entire solar system, were dense enough to show up as dark silhouettes against the background glow. Hester and his team realized what they were seeing. These were regions where gas and dust were so dense they had begun to collapse under their own gravity. These were not just clouds, they were cocoons. Inside these structures, which the team dubbed EGGs, evaporating gaseous globules, an acronym that was both scientifically descriptive and delightfully appropriate, stars were in the process of being born. Embryonic stars, surrounded by the remnants of their natal clouds, caught in the act of formation. The discovery was profound. For years, astronomers had theorized about star formation, building models based on observations of nearby stellar nurseries like the Orion Nebula. But here, for the first time, Hubble had captured star formation with unprecedented clarity in a unique orientation. Unlike the Orion Nebula, which we see face on, the Eagle Nebula presented a side view, allowing astronomers to see the 3-dimensional structure of a star-forming region. They could see the hot young stars, located just above the top of the image, the cavity they had carved out with their intense radiation, the evaporating surface of the molecular cloud, and the dense pillars themselves, still intact but slowly being eroded away. Hester described the process in terms that made the cosmic comprehensible. Imagine, he said, wind blowing across a desert landscape. The wind carries away loose sand, but where there are rocks, heavier and denser than their surroundings. Those remain behind as the sand around them erodes. Eventually, the rocks are exposed, standing atop pillars of more resistant material that sheltered them from the wind. That's essentially what was happening in M16, except instead of wind, it was ultraviolet radiation from massive young stars. And instead of rocks, it was these dense globules of gas where new stars were forming. This process had a name: photoevaporation. The intense ultraviolet light from the cluster of hot, massive stars above the pillars, stars that had formed from this same molecular cloud just a few million years earlier, was literally evaporating the less dense gas and dust, boiling it away into space. You could see the evidence in the image itself: ghostly streamers of gas bleeding off the surfaces of the pillars, illuminated by the very radiation that was causing them to evaporate. The implications were startling. If a star was still forming when photoevaporation exposed it, still growing by pulling in more material from its surrounding cloud, the sudden loss of that cloud would halt its growth. The star's mass would be frozen at whatever it had managed to accumulate before being uncovered. Some of the EGGs visible in the Hubble image contained protostars massive enough to eventually become full-fledged stars. Others might never make it, their supply of material cut off before they could gather enough mass to ignite fusion in their cores. This meant the environment in which a star formed could fundamentally determine what kind of star it became. Star formation wasn't just about gravity pulling gas together until fusion ignited. It was a complex interplay between gravity, which tried to build stars bigger and bigger, and radiation, which could interrupt that process, limiting how large a star could grow. The Pillars of Creation offered a laboratory for studying this process in action. When the image was released to the public, the response was immediate and overwhelming. This wasn't just another pretty picture from Hubble. This was art and science merged into something that spoke to people on a visceral level. The pillars looked ancient, timeless, like monuments from a civilization far beyond human imagination. They looked fragile and temporary, columns of smoke and dust that might dissipate at any moment. They looked creative and destructive simultaneously, places where stars were born even as the pillars themselves were slowly dying. Within days, the image appeared in newspapers and magazines around the world. Space.com would later name it one of the top 10 photographs from Hubble, but that seems like an understatement. The Pillars of Creation transcended the realm of scientific imagery to become a cultural icon. It appeared on postage stamps in multiple countries. It was printed on t-shirts, coffee mugs, and posters. It hung in classrooms and inspired countless students to pursue astronomy. It appeared in films and television shows, a visual shorthand for the vastness and beauty of the cosmos. National Geographic, marking the image's 20th anniversary in 2015, noted that it had become perhaps the most recognizable astronomical image in history, featured on everything from dorm room walls to museum exhibitions. The name itself, Pillars of Creation, became part of the cultural lexicon, evoking a sense of cosmic grandeur and the eternal cycle of birth and death playing out on scales almost too vast to comprehend. But beyond the cultural impact, the scientific value of the image and the subsequent observations it inspired was immense. The Pillars of Creation became one of the most studied regions in space. Astronomers used different wavelengths to probe the structures: X-rays to find the young stars themselves, infrared to see through the dust, radio waves to map the cold molecular gas. Each new observation added another piece to the puzzle, building a more complete picture of what was happening in this stellar nursery. In 2007, the Chandra X-ray Observatory detected over 1,700 individual X-ray sources in the broader Eagle Nebula region. These X-ray sources were young stars, their hot surfaces and active regions emitting high-energy radiation. The pattern was revealing. X-ray sources didn't cluster within the pillars themselves, but were scattered throughout the nebula. This made sense. The protostars buried within the dense EGGs weren't yet hot enough to emit significant X-rays. Only after they emerged, after the pillars eroded away and exposed them, would they begin to glow in X-ray light. Then came a discovery that changed everything we thought we knew about the pillars of creation. In 2007, the Spitzer Space Telescope, observing in infrared wavelengths, detected something ominous: a cloud of unusually hot dust in the vicinity of the pillars. The temperature and distribution suggested this wasn't just dust heated by normal stellar radiation. It looked like a shock wave. Specifically, it looked like the expanding debris cloud from a supernova explosion. The astronomers ran the calculations backward. If this was indeed a supernova shockwave, it would have originated from a massive star that exploded roughly 8,000 to 9,000 years ago. The light from that explosion would have reached Earth sometime between 1,000 and 2,000 years ago, a brief flash in Earth's sky that might have been visible to our ancestors, perhaps noticed by ancient Chinese astronomers who kept meticulous records of guest stars, or perhaps lost to history if it occurred during cloudy weather or simply wasn't bright enough to attract attention. But light travels faster than matter. The shockwave itself, expanding outward at tremendous speeds, but still far slower than light, would have taken longer to reach the pillars. Much longer. If the calculations were correct, the shockwave would have hit the pillars of creation roughly 1,000 years ago. And when a supernova shockwave hits a delicate structure, like these columns of gas and dust, there's only one possible outcome: total destruction. This means that the pillars of creation, those monuments we've been admiring for decades, those structures that became the face of cosmic beauty, might not exist anymore. They might have been torn apart and scattered 1,000 years ago, while medieval Europe was experiencing the Viking Age, while the Song dynasty ruled China, while the ancestral Puebloans were building their cliff dwellings in what would become the American Southwest. We wouldn't know. We can't know. Because the light showing us that destruction hasn't reached us yet. We're seeing the pillars as they were 6,500 years ago, blissfully unaware of a cataclysm that might have already swept them away. The light from their destruction is still in transit, traveling toward us at 186,000 miles per second, and it won't arrive for another millennium. We're watching cosmic history on a profound delay, seeing monuments that might be nothing more than memory. Not everyone accepted this interpretation. Other astronomers disputed the findings, arguing that a supernova powerful enough to create that shockwave should have produced much stronger radio and X-ray emissions than what was observed. More likely, they suggested, the hot dust was heated by powerful stellar winds from massive stars in the region, not by a supernova. If that's the case, the pillars would erode more gradually, over millions of years, rather than being destroyed in a single violent event. This scientific debate added a new dimension to the pillars of creation. Were we looking at structures that still existed, or at ghosts? Cosmic photographs of monuments that had already been swept away by forces we couldn't yet detect. The uncertainty only deepened the mystique. Either way, the pillars we observed were real in the moment, captured by Hubble's cameras, frozen in time like an ancient photograph. Genuine evidence of the way the universe was 6,500 years ago, even if we couldn't know whether they'd survived. Into the present day. In 2014, on the eve of Hubble's 25th anniversary, astronomers revisited the pillars of creation with the telescope's newer Wide-Field Camera 3, installed by astronauts during a servicing mission in 2009. The new camera was more sensitive, captured a wider field of view, and could observe in both visible and infrared wavelengths. The resulting images were sharper, more detailed, and more colorful than the original 1995 version. The new visible light image revealed more of the base of the pillars, showing how they connected to the larger molecular cloud. The colors were more vibrant. Oxygen glowed blue, hydrogen and nitrogen shone green, and sulfur radiated in orange and red. The finger-like projections at the tips of the pillars were more clearly defined, and the streaming tendrils of evaporating gas were more dramatic. But perhaps more significantly, Hubble also captured the region in near-infrared light, wavelengths just beyond the red end of the visible spectrum that can penetrate some of the dust. In this infrared view, the pillars transformed. Instead of dark, opaque columns, they became translucent, wispy structures. The background, previously mostly empty, was suddenly filled with stars, thousands of them, previously hidden behind or within the dust. Some of these stars were behind the pillars, their light filtering through the semi-transparent gas. Others were embedded within the pillars themselves, young stars still surrounded by their natal material. This infrared preview was tantalizing. If Hubble, which could only see the nearest edge of the infrared spectrum, could reveal so many hidden stars, what might a telescope optimized for infrared observation discover? What secrets were still concealed within the deepest, coldest, densest regions of the pillars, where even Hubble's infrared capabilities couldn't reach? The answer would come 8 years later, from a telescope that was, at that moment, being prepared for launch at a facility in French Guiana, a telescope that would revolutionize our view not just of the pillars of creation, but of the universe itself. Understanding the Eagle Nebula. Before we can truly appreciate what makes the pillars of creation so extraordinary, we need to understand the larger environment they inhabit. The Eagle Nebula, cataloged as Messier 16 or M16, and also designated as NGC 6611 for the star cluster at its heart, is far more than just the pillars themselves. It's a vast, complex region of stellar birth, spanning roughly 70 by 55 light-years of space, located approximately 6,500 to 7,000 light-years from Earth, in the constellation Serpens, the Serpent. To put that distance in perspective, imagine traveling at the speed of light, moving at 186,282 miles every single second, fast enough to circle Earth 7.5 times in 1 second, fast enough to reach the moon in just over 1 second, fast enough to reach the sun in about 8 minutes, if you traveled at sheep. This incomprehensible speed for 6,500 years, never stopping, never slowing, you would finally arrive at the Eagle Nebula. That's how far away this stellar nursery is from our quiet corner of the galaxy. And yet, despite this enormous distance, we can see it. On a dark night, far from city lights, with a good pair of binoculars or a small telescope, you can spot the Eagle Nebula yourself. It appears as a faint, glowing patch of light in the summer sky, most clearly visible in July. You won't see the detail that Hubble revealed, of course. You won't make out the pillars themselves without a much larger telescope and excellent atmospheric conditions. But you'll see the glow of ionized hydrogen gas, energized by the young stars being born within, and you'll know that you're looking at a place where the universe is actively creating new suns. The nebula itself is what astronomers classify as a diffuse emission nebula. More specifically, an H2 region, pronounced H2 region, referring to ionized hydrogen. These regions are common throughout galaxies, marking sites of active star formation. They form when massive, hot young stars emit intense ultraviolet radiation that ionizes the surrounding hydrogen gas, causing it to glow. The characteristic reddish-pink color of emission nebulae in visible light comes from the specific wavelength of light emitted when ionized hydrogen atoms recapture electrons and drop to lower energy states, a wavelength called H-alpha at 656.3 nanometers. But the Eagle Nebula is also partially a dark nebula, containing regions of cold, dense molecular gas and dust that are opaque even to visible light. These dark regions appear as black silhouettes against the glowing background, blocking our view of stars and nebula behind them. The pillars of creation themselves are examples of these dark structures, illuminated from behind and from the sides by the glow of ionized gas, but dark in their cores where the dust is densest. At the heart of the Eagle Nebula lies NGC 6611, an open star cluster containing several hundred stars, many of them young, massive, and extremely hot. These stars formed from the same giant molecular cloud that birthed the pillars of creation, but they formed earlier, a few million years ago, and have already burned through the material surrounding them. Now, free of their natal clouds, they shine fiercely in ultraviolet and visible light. It's these stars that are the architects of the structures we see. Their intense radiation creates a bubble in the surrounding molecular cloud, carving out a cavity by photoevaporation. As the lower density gas boils away under this radiation pressure, denser knots and clumps resist longer, forming pillars, columns, and elephant trunk structures that point back toward the source of the radiation. The pillars of creation are just one such structure, perhaps the most dramatic and well-positioned for our viewing angle, but they're far from alone. Throughout the Eagle Nebula, similar formations rise from the edges of the molecular cloud, each one a testament to the interplay between creation and destruction. The nebula's name, as mentioned, comes from its overall shape, which to some observers resembles an eagle with outstretched wings. This interpretation requires some imagination and a certain configuration of viewing conditions, but once you see it, it's hard to unsee. The dense dark clouds form what might be considered the body and wings of the eagle, while the star cluster NGC 6611 marks the eagle's eye or head. The pillars of creation, in this interpretation, might be thought of as the eagle's talons or claws, reaching forward from the wing. American astronomer Robert Burnham Jr., in his influential 3-volume Burnham's Celestial Handbook, published in the 1970s, offered another poetic interpretation. He saw the central pillar as resembling the silhouette of a star queen, a majestic figure rising from the cosmic landscape. This interpretation, while less commonly used than the eagle reference, adds another layer to the rich cultural tapestry surrounding this region. The Eagle Nebula lies in what astronomers call the Sagittarius arm of the Milky Way, one of the galaxy's spiral arms. This means it's not in our immediate neighborhood. We reside in the Orion Spur, sometimes called the Orion Arm, a minor spiral feature between two major arms. The Eagle Nebula, being 6,500 light-years away, is at a considerable distance within our galaxy, though still very much within the Milky Way itself. For comparison, the Milky Way's disk is roughly 100,000 light-years across, so the Eagle Nebula, while far from us, is actually relatively nearby in galactic terms. This proximity is part of what makes the Eagle Nebula, and the pillars of creation within it, such valuable targets for study. They're close enough that even modest-sized telescopes can observe significant detail. They're close enough that individual stars can be resolved and studied. They're close enough that we can map the three-dimensional structure of the region, understanding not just what we see projected on the plane of the sky, but how these structures extend in depth, toward us and away from us, through space. The molecular cloud from which the Eagle Nebula's stars are forming is massive, containing many thousands of solar masses of material. Most of this mass is in the form of molecular hydrogen, H2, the most common molecule in the universe after H2+ and helium. Each molecule consists of two hydrogen atoms bound together. This molecular hydrogen is incredibly cold, typically just 10 to 20 degrees above absolute zero, cold enough that if you could somehow stand in the midst of it, you would freeze solid almost instantly. The dust mixed with this gas plays multiple crucial roles. It helps cool the gas by radiating away heat, allowing the clouds to collapse more easily under gravity. It shields the interior of the clouds from destructive ultraviolet radiation, creating protected environments where star formation can proceed. And it absorbs shorter wavelengths of light while allowing longer wavelengths to pass through, which is why visible light telescopes see the pillars as dark and opaque, while infrared telescopes can peer inside. The dust itself is remarkable. These aren't dust particles like the ones under your bed. They're microscopic grains, typically smaller than the wavelength of visible light, composed of various materials. Some are silicates, similar to the minerals found in rocks on Earth. Others are carbon-based, including grains of graphite and complex organic molecules. Some grains are coated with ices, frozen water, carbon dioxide, methane, and ammonia that have condensed out of the gas in the frigid environment of space. These dust grains serve as the surface upon which more complex molecules can form. In the dense cores of molecular clouds, hydrogen atoms landing on dust grain surfaces can combine to form H2. More complex organic molecules, including the precursors to amino acids and other building blocks of life, can assemble on these cosmic dust grains. When stars eventually form and planets coalesce around them, these dust grains and the molecules they carry become part of those planetary systems. The organic molecules in comets, asteroids, and even planets like Earth may have originated on dust grains in stellar nurseries, not unlike the Eagle Nebula. Throughout the Eagle Nebula, star formation is happening at different stages and different rates. Some regions have already produced their stars, which now shine brightly, clearing away the gas and dust that once surrounded them. Other regions, like the pillars of creation, are still actively forming stars, with dense cores collapsing under gravity, even as the pillars themselves are slowly eroded away. Still other regions are quiescent, cold, dark clouds that haven't yet begun to collapse, waiting perhaps for some trigger, a shock wave from a nearby supernova, or the compression from a passing spiral density wave, to push them over the edge into gravitational instability. This progression is part of what makes stellar nurseries, like the Eagle Nebula, so valuable for study. We can see multiple stages of star formation happening simultaneously in the same region. We can see clouds that haven't yet collapsed, clouds in the process of collapsing, protostars just beginning to shine, young stars still surrounded by their natal material, and finally, mature stars that have cleared their surroundings. It's like looking at a forest and seeing saplings, young trees, mature trees, and old trees all in the same view, allowing us to understand the full life cycle by observing many individuals at different stages. The Eagle Nebula also serves as a reminder of the cycle of stellar life and death. The material in this nebula, the gas and dust from which new stars are forming, wasn't always in this form. Much of it was forged in earlier generations of stars, stars that lived, burned, and eventually died, returning their processed material to the interstellar medium. The oxygen glowing in those beautiful blue-green hues in Hubble's images, that oxygen was created in the cores of massive stars through nuclear fusion, then scattered into space when those stars exploded as supernovae. The carbon in the dust grains, created in stars and puffed into space through stellar winds. The iron that might someday form rocky planets around the stars being born in the pillars, also forged in stellar cores and distributed by supernovae. In this way, the Eagle Nebula is not just creating stars. It's recycling the material of the universe, taking the debris of earlier stellar generations and incorporating it into new stars and potentially new planetary systems. The atoms being gathered into protostars in the pillars of creation right now have a history that stretches back billions of years, through multiple cycles of stellar birth and death. And billions of years from now, when these new stars eventually die, they'll return their own processed material to the next generation, continuing the cycle. This perspective adds a poignant dimension to images of the Eagle Nebula. We're not just seeing a static structure, beautiful but unchanging. We're seeing one moment in a vast cosmic cycle, a cycle that has been ongoing for most of the universe's history and will continue for billions of years to come. The pillars we see are temporary, ephemeral on cosmic timescales, but the process they represent, the transformation of diffuse gas into new stars, is as fundamental and eternal as gravity itself. Anatomy of the pillars. Now let's focus specifically on the pillars of creation themselves, understanding their structure, composition, and the forces that shape them into the magnificent formations captured by our telescopes. The three main pillars visible in the iconic Hubble image are enormous by any measure. The tallest pillar, the one on the left in most orientations of the image, stretches approximately 4 light-years from its base to its tip. The middle pillar is slightly shorter, about 3 light-years tall, and the rightmost pillar measures approximately 2 light-years. To give you a sense of scale, 4 light-years is roughly the distance from our Sun to the nearest star, Proxima Centauri. One of these pillars could span the gap between our solar system and our nearest stellar neighbor with room to spare. But light-years, while accurate, are hard to truly comprehend. Let's try another approach. Light travels at 186,282 miles per second, or roughly 5.88 trillion miles in a year. The tallest pillar, at 4 light-years, is approximately 23.5 trillion miles tall. If you could somehow drive a car at highway speed, 60 miles per hour, straight up this pillar without stopping, the journey would take about 45 million years. The pillar is so large that if we could shrink the entire structure down to where 1 mile equaled 1 inch, the pillar would still stretch over 200 miles tall, roughly the distance from New York to Denver. The finger-like protrusions extending from the tops of the pillars, those structures containing the evaporating gaseous globules where stars are forming, are themselves larger than our entire solar system. If we define the solar system's size as extending to the heliopause, where the sun's solar wind meets the interstellar medium, about 120 astronomical units, or 120 times the distance from Earth to the sun, these EGGs dwarf it. Each is several hundred to several thousand astronomical units across. Inside just one of these structures, you could fit dozens of solar systems laid end to end. The pillar's composition is primarily molecular hydrogen, H2, with traces of other molecules and atoms mixed in. Molecular hydrogen makes up roughly 70 to 75% of the mass. Helium accounts for about 25%, mirroring the overall composition of the universe. The remaining few percent consists of heavier elements, what astronomers somewhat confusingly call metals, even though most aren't metals in the chemical sense. This includes carbon, nitrogen, oxygen, silicon, iron, and a host of other elements, many of them locked up in dust grains. The density within the pillars varies dramatically. At the outer edges, where they're being actively photoevaporated, the gas is relatively thin, perhaps a few hundred to a few thousand molecules per cubic centimeter. This might sound dense compared to the hard vacuum of space, far from any stellar nurseries, which contains only a handful of atoms per cubic centimeter, but it's extraordinarily tenuous by Earth standards. Our atmosphere at sea level contains about 2.5 × 1019 molecules per cubic centimeter, roughly 100 trillion times denser than the outer edges of the pillars. Deeper within the pillars, in the regions shielded from direct radiation, the density increases. In the densest cores, particularly within the EGGs themselves, the density can reach 1 million molecules per cubic centimeter, or even higher. These cores are the regions that will eventually collapse to form stars, gathering more and more material until the central pressure and temperature become high enough to ignite nuclear fusion. The temperature also varies. The surfaces of the pillars, exposed to intense ultraviolet radiation from the nearby cluster of hot stars, can be relatively warm by interstellar standards, reaching several hundred to perhaps 1,000 degrees Kelvin. But just beneath the surface, shielded from direct radiation, the temperature drops dramatically. In the cores of the pillars, the gas is extraordinarily cold, typically just 10 to 20 degrees above absolute zero, 10 to 20 Kelvin, or about 441 to 423 degrees Fahrenheit, or 263 to 253 degrees Celsius. At these temperatures, all motion almost ceases at the molecular level. There's barely enough thermal energy for molecules to vibrate or rotate. This extreme cold is crucial for star formation. For a cloud of gas to collapse under its own gravity, its gravitational potential energy must exceed its thermal energy. Hot gas resists collapse because the random motion of molecules creates an outward pressure that counteracts gravity. Cold gas has minimal thermal pressure, allowing gravity to win. This is why stars form in the coldest, densest regions of molecular clouds. The pillars, particularly their cores, represent some of the coldest material in the universe. The pillar-like shape itself is a direct result of photoevaporation, the same process that creates the streamers of gas bleeding off the structure's surfaces. When a massive molecular cloud is exposed to intense ultraviolet radiation from nearby hot stars, the radiation doesn't evaporate the cloud uniformly. Regions that happen to be denser than their surroundings resist the radiation longer, acting like cosmic umbrellas that cast shadows in the ultraviolet light. Here's how it works. Ultraviolet photons from the hot stars strike the surface of the molecular cloud, ionizing hydrogen atoms, splitting them into protons and electrons, and heating the gas. The hot, ionized gas expands away from the cloud surface, creating an outflow. Where the cloud is uniform in density, this erosion proceeds smoothly. But where there are denser knots or clumps, those regions erode more slowly, leaving behind pillars and columns. The pillar points back toward the source of the ionizing radiation, much like a windsock points in the direction the wind is coming from. The dense core of the pillar casts a shadow in the ultraviolet light, protecting the gas behind it, from our viewing perspective, from direct radiation. This protected gas erodes more slowly than the surrounding material, creating the long, finger-like extensions we see. Think of it like an analogy with water erosion. If you've ever seen Badlands or hoodoos, those strange rock formations, in desert environments where a harder cap rock sits atop softer material, you've seen a terrestrial version of this process. Rain and wind erode the soft material away, but the cap rock protects the column beneath it, leaving tall spires of rock topped with flat stones. The pillars in M16 work on the same principle, except the erosion is happening through photoevaporation rather than wind and rain, and the timescales are millions of years rather than thousands. The lava-like structures visible along the edges of the pillars in James Webb images, which we'll discuss in more detail later, are jets and outflows from protostars. As a star forms, not all the material falling onto it gets accreted. Some is ejected in powerful bipolar jets, streams of material that shoot out from the star's poles at speeds of hundreds of kilometers per second. When these jets slam into the surrounding cloud material, they create shock waves that heat and excite the gas, causing it to glow. The wavy, undulating appearance comes from the interaction between these jets and the ambient material, creating structures that look like streams of glowing lava flowing along the pillar's surface. The pillars are not static. They're slowly being destroyed even as we observe them. The intense ultraviolet radiation from NGC 6611 is gradually eroding them away, boiling off material at a rate of roughly a few Earth masses per year. This might not sound like much, but over millions of years, it adds up. The pillars are losing mass, getting smaller, slowly fading away. Some models suggest the pillars might only survive for another million years or so before they're entirely dispersed. That might seem like a long time by human standards, but it's just a blink of an eye in cosmic terms. If the Milky Way's age of about 13 billion years were compressed into a single 24-hour day, the pillars would exist for less than 2 seconds. But their destruction is also their purpose in a sense. As the pillars erode, they expose the EGGs and the protostars within. These stars, initially buried deep within their natal clouds, gradually emerge into the light. The photoevaporation that destroys the pillars also regulates the star's growth, determining how massive they'll become by limiting how much material they can accrete before their surrounding cloud disperses. The orientational fortune that allows us to see the pillars so clearly is also worth noting. we're seeing them almost edge on, which gives us a dramatic silhouette view. If we saw them face on, they might just appear as bright knots in a more diffuse nebula. If we saw them from directly behind, from the perspective of NGC 6611, we might see mostly the glowing ionized surface with the dark pillars hidden behind it. But our viewing angle is nearly perfect for appreciating their three-dimensional structure, seeing them as columns rising from the molecular cloud, with stars forming at their tips and along their lengths. There are also smaller pillar structures throughout the Eagle Nebula beyond the three famous ones. If you look at wider field images of M16, you can see numerous other elephant trunks, columns, and cometary globules scattered throughout the nebula. The pillars of creation are simply the most dramatic and photogenic of these features, but they're part of a larger pattern of structures shaped by the same physical processes. Interestingly, there's a smaller feature visible in some images of the pillars of creation, a dark, finger-like structure at the lower right of the frame. This might be a miniature version of the larger pillars, or it could be another structure at a different distance within the nebula. The three-dimensional geometry of the region is complex, and not everything we see is at the same distance from us. Some structures might be in the foreground, others in the background, creating a layered view of the stellar nursery. The material composition of the pillars also tells a story of earlier stellar generations. The elements heavier than hydrogen and helium didn't exist in the early universe. They were created through nuclear fusion in the cores of earlier stars, then distributed into space through supernova explosions and stellar winds. The presence of these elements in the Eagle Nebula's pillars means that earlier generations of stars lived, burned, and died in this region of the galaxy, enriching the gas that would later collapse to form the stars we see today. This means that when we look at the pillars of creation, we're seeing recycled stardust, material that has been through multiple cycles of stellar birth and death. The atoms in those pillars carry the history of the galaxy encoded in their very existence. And the stars being born there now will someday die and contribute their own processed material to future generations of stellar nurseries, continuing the cycle that has been ongoing since the first stars ignited billions of years ago. In this sense, the pillars of creation are aptly named. They are places of creation, yes, but they're also monuments to the universe's endless capacity for renewal and transformation. They remind us that nothing in the cosmos is truly permanent, that even the most stable-seeming structures are subject to change over time, and that from ending comes new beginning, from death comes new life, in an eternal cycle that connects the first stars to the last. Hubble's technology and vision. To understand what Hubble revealed about the pillars of creation, and what it couldn't reveal, we need to understand how the telescope works and what wavelengths of light it observes. The Hubble Space Telescope, launched aboard the Space Shuttle Discovery on April 24, 1990, was designed as a general-purpose observatory capable of studying the universe across a broad range of wavelengths. Hubble orbits Earth at an altitude of roughly 340 miles, 547 kilometers, completing one orbit approximately every 95 minutes. This low Earth orbit places it above the bulk of Earth's atmosphere, which is crucial for its mission. Earth's atmosphere, while essential for life, is a nightmare for astronomers. It blurs images through a phenomenon called seeing, caused by turbulence in the air. It absorbs most ultraviolet and infrared wavelengths, blocking them from reaching ground-based telescopes. And it creates a diffuse background glow that makes observing faint objects more difficult. By operating above the atmosphere, Hubble avoids all these problems. It can observe ultraviolet wavelengths that never reach the ground. Its images are diffraction limited, meaning their sharpness is determined only by the size of the mirror and the wavelength being observed, not by atmospheric turbulence. And it can observe extremely faint objects against the black background of space without interference from atmospheric glow. Hubble's primary mirror is 2.4 meters, about 7.9 feet in diameter. this might not sound enormous, compared to modern ground-based telescopes, which can have mirrors over 30 feet across. But Hubble's space-based location gives it advantages that more than compensate for its relatively modest size. The mirror was polished to incredible precision, smooth to within about 10 nanometers, or roughly 1/65th the wavelength of red light. This precision is necessary to achieve diffraction-limited performance. The telescope's wavelength range is impressive. Hubble can observe light from about 90 nanometers in the far ultraviolet through the entire visible spectrum, roughly 380 to 750 nanometers, and into the near infrared up to about 2,500 nanometers, or 2.5 microns. This gives Hubble a view spanning more than 25 times in wavelength, from ultraviolet wavelengths that would cause severe sunburn if you were exposed to them, to infrared wavelengths that you can feel as heat from a warm object. When Hubble observed the Pillars of Creation in 1995, it used the Wide Field and Planetary Camera 2, or WFPC-2. This instrument, installed during the first servicing mission in 1993, used charge-coupled devices, CCDs, as detectors, the same technology used in digital cameras, but highly specialized for astronomical observations. WFPC-2 had 4 cameras, 3 wide-field cameras arranged in an L shape, and 1 planetary camera with higher magnification positioned in the 4th corner. The 32 images combined to create the famous 1995 Pillars of Creation photo were taken through 3 different narrowband filters, each isolating light from a specific emission line. One filter captured H-alpha light from hydrogen at 656.3 nanometers. Another isolated the emission line from singly ionized sulfur at 673 nanometers. The third captured light from doubly ionized oxygen at 500.7 nanometers. Each filter produced a grayscale image showing the distribution of that particular element. These grayscale images were then combined and assigned colors. Typically, the shortest wavelength, the blue-green oxygen, was assigned a blue color in the final image. The middle wavelength, red hydrogen, was assigned green, and the longest wavelength, the red-orange sulfur, was assigned red. This is called a false color image, because the colors don't represent what the human eye would see, but rather are chosen to highlight the different elements and make subtle structures more visible. This technique is powerful because it reveals the nebula's physical structure and composition. Oxygen, which requires more energy to doubly ionize, appears in the hottest, most energetic regions. Hydrogen, which is abundant everywhere and easily ionized, shows the overall distribution of gas. Sulfur, which requires moderate energy to singly ionize, traces regions of intermediate temperature and ionization. By looking at how these 3 elements are distributed, astronomers can understand the temperature structure, the ionization state, and the physical conditions throughout the nebula. What Hubble revealed, with these visible light observations, was stunning. The pillars themselves appeared as dark silhouettes, their dense cores opaque to visible light. The edges were illuminated with intricate detail, showing the convoluted surfaces where photoevaporation was actively occurring. The ghostly streamers of evaporating gas were clearly visible, demonstrating the dynamic nature of the region. And the EGGs showed up as dark knots against brighter backgrounds, their dense material too cool and opaque to glow in visible light. But visible light has limitations. The dust that permeates the pillars absorbs and scatters visible wavelengths very efficiently. A blue photon trying to pass through a dust cloud has a high probability of being absorbed by a dust grain or scattered in a random direction. Even red photons, which are somewhat better at penetrating dust than blue ones, struggle to make it through the densest regions. This means that what Hubble showed us in visible light was essentially the surfaces of the pillars. We could see their outsides, illuminated by the glow of ionized gas and starlight, but we couldn't see into their interiors where the real action of star formation was occurring. The protostars buried within the EGGs were invisible in visible light, hidden behind walls of dust that might contain billions of Earth masses of material. In 2014, when Hubble revisited the pillars with its newer Wide-Field Camera 3, WFC-3, installed during the final servicing mission in 2009, it did include infrared observations. WFC-3 could observe in near-infrared wavelengths up to about 1.7 microns, wavelengths that can penetrate more dust than visible light. The resulting infrared image transformed the pillars from opaque columns to semi-transparent structures, revealing hundreds of stars that were completely invisible in the visible light images. But even this infrared view had limitations. WFC-3's near-infrared capability extended only to about 1.7 microns, just into the near-infrared part of the spectrum. Many of the protostars embedded in the pillars emit most of their light at longer wavelengths, in the mid-infrared around 5 to 20 microns. Hubble's instruments simply weren't sensitive to these longer wavelengths. The telescope's mirrors were kept at about 15 degrees Celsius, about 59 degrees Fahrenheit, warm enough that they emitted their own infrared radiation at these longer wavelengths, which would swamp any signal from astronomical sources. This is a fundamental limitation of Hubble's design. The telescope was optimized for ultraviolet and visible light, with some near-infrared capability added through later instruments. But to observe the mid-infrared efficiently, you need a cold telescope, kept at temperatures below about 50 Kelvin, 223 Celsius, or 370 Fahrenheit. At those cold temperatures, the telescope's own thermal emission becomes negligible compared to the faint infrared glow from astronomical objects. Hubble also couldn't directly image individual forming stars within the pillars. Even in its infrared observations, most of what we saw were stars that had already cleared much of their surrounding material, allowing their light to escape. The youngest protostars, still deeply embedded in their natal cocoons, remained hidden. We knew they had to be there based on the structure of the EGGs and on observations at other wavelengths, but Hubble couldn't show them to us directly. Despite these limitations, Hubble's contribution to our understanding of the pillars of creation cannot be overstated. It revealed the detailed structure of the pillars, showing us how photoevaporation sculpts these magnificent columns. It identified the EGGs where stars were forming and showed us that the environment of star formation matters. That radiation from nearby stars can regulate and limit the growth of forming stars. It captured images of such beauty and power that they transformed public perception of astronomy, showing that scientific observations could also be works of art. Hubble's visible light observations also had advantages that infrared observations couldn't match. Visible light reveals different physical processes than infrared. The glowing edges of the pillars, where hot ionized gas streams away into space, show up best in visible wavelengths. The delicate structure of the photoevaporated surface is most apparent in visible light, and the background stars, many of them hot blue stars from the NGC 6611 cluster, are brightest in visible and ultraviolet wavelengths. This is why the comparison between Hubble and James Webb is so compelling. They're not competing visions, one superior to the other. They're complementary perspectives, each revealing aspects of the pillars that the other cannot. Hubble shows us the outside, the visible surface, the boundary between the dense molecular cloud and the hot ionized gas surrounding it. Webb shows us the inside, the cold, dense cores, the embedded protostars that Hubble couldn't detect. Together, these two telescopes provide a complete picture, like using both your eyes to perceive depth, or listening to a symphony with both ears to appreciate its full richness. Neither view alone tells the whole story, but combined, they reveal the pillars of creation in unprecedented detail, from their glowing ionized surfaces down to their cold, star-forming cores. Hubble also demonstrated the power of servicing missions. Over its 30-plus years in orbit, astronauts visited Hubble 5 times, replacing instruments, upgrading computers, installing new gyroscopes, and performing repairs. Each servicing mission effectively created a new, more powerful telescope. The Hubble that imaged the pillars in 1995 was far more capable than the Hubble launched in 1990, which suffered from a mirror flaw that was corrected during the first servicing mission. The Hubble that revisited them in 2014 was more capable still, with newer cameras and expanded wavelength coverage. This upgrade path is one that James Webb cannot follow. Webb orbits not Earth, but the Sun, at a location about 1 million miles from Earth called the Second Lagrange Point, L2. At that distance, no servicing mission is currently possible with existing technology. Webb was designed to operate for at least 5 to 10 years without servicing, and in fact, due to the precise launch and efficient trajectory corrections, it has enough fuel to potentially operate for 20 years or more. But when it eventually fails, whether from a critical component breaking down or from running out of fuel for station keeping, it will mark the end of Webb's mission. There will be no astronauts arriving to fix it. This makes Webb's observations all the more precious. Every image, every spectrum, every discovery must come in this single window of operation. Hubble, by contrast, served as a platform that could be updated and upgraded, adapting to new scientific priorities and incorporating new technologies. Both approaches have merits, but they represent different philosophies of space-based astronomy. Hubble's legacy, particularly with images like the Pillars of Creation, is secure. It's shown us a universe of unexpected beauty, and it's demonstrated that astronomy isn't just about abstract data and equations. It's about revealing the cosmos in ways that speak to something fundamental in human nature: our sense of wonder, our aesthetic appreciation of beauty, our desire to understand our place in the vastness of space and time. When people see the Pillars of Creation, they're moved not just intellectually, but emotionally. And that emotional connection, that sense of awe and wonder, is what inspires the next generation of scientists, engineers, and explorers. As we now turn to James Webb and its revolutionary view of the same region, we'll see how building on Hubble's foundation, using different wavelengths and more advanced technology, we can peel back another layer of mystery and see deeper into the process of star formation than ever before. Enter James Webb, a revolution. On December 25th, 2021, Christmas Day, an Ariane 5 rocket lifted off from the Guyana Space Center in Kourou, French Guiana, carrying the most ambitious, complex, and expensive science instrument ever constructed by humanity. The James Webb Space Telescope, decades in planning and development, billions of dollars in cost, was finally heading to space. Unlike Hubble, which orbits Earth every 95 minutes at a comfortable distance of just a few hundred miles, Webb was destined for a location much farther away: the second Sun-Earth Lagrange point, designated L2. This point lies approximately 1.5 million kilometers from Earth, about 1 million miles, roughly 4 times farther than the Moon. At this location, the gravitational pulls of the Sun and Earth combine in such a way that an object placed there can orbit the Sun with the same period as Earth, remaining in a relatively fixed position, relative to our planet. The journey took 30 days. For the first 3 days, Webb traveled as far as the Moon's orbit, covering about a quarter of the total distance. The remaining 3/4 of the journey, farther into space than any human has ever ventured, took the rest of the month. During this time, one of the most complex deployment sequences ever attempted in space unfolded like an intricate origami reverse engineered into reality. Webb had to fold to fit inside the Ariane 5's payload fairing. Its primary mirror, 6.5 meters, about 21.3 feet in diameter, was segmented into 18 hexagonal pieces that folded backward for launch. Its sun shield, roughly the size of a tennis court at 22 by 14 meters, was folded up like an umbrella. Dozens of deployment mechanisms, hundreds of release devices, and miles of cabling all had to work perfectly for the telescope to function. And remarkably, everything worked. The sun shield deployed flawlessly, unfurling its 5 layers of specialized material to create a barrier between the hot sun-facing side of the spacecraft and the cold telescope-facing side. The secondary mirror swung into position on its boom. The primary mirror segments unfolded, first one wing, then the other, clicking into place with barely a millimeter of error. The telescope that arrived at L2 in late January 2022 was fully deployed and ready, after a nail-biting month where a single failure could have meant the end of the mission. Why L2? The answer lies in Webb's mission requirements. Webb is an infrared telescope designed to observe wavelengths from about 0.6 microns at the red edge of visible light to 28.5 microns in the mid-infrared. To detect these wavelengths from faint, distant astronomical sources, Webb's instruments need to be extraordinarily cold, below about 50 Kelvin, 223 Celsius, or 370 Fahrenheit. At warmer temperatures, the telescope itself would emit enough infrared radiation to swamp the faint signals from space. L2 provides several advantages for achieving and maintaining these cold temperatures. First, it allows the sun shield to block light and heat from the sun, earth, and moon simultaneously, all of which lie in the same general direction from Webb's perspective. The telescope and instruments face away from these heat sources, looking out into the cold darkness of space. The sun shield, with its 5 layers of Kapton coated with aluminum and silicon, provides extraordinary insulation. The sun-facing side can reach temperatures over 100 degrees Celsius, about 212 Fahrenheit, hot enough to boil water. The telescope-facing side stays below 50 Kelvin, cold enough that nitrogen, which makes up most of Earth's atmosphere, would freeze solid. L2 also provides an excellent viewing situation. Because it follows Earth in its orbit around the Sun, Webb maintains a roughly constant position relative to Earth, always in Earth's midnight sky, about 1.5 million kilometers away. This allows continuous communication through NASA's Deep Space Network, a collection of large radio antennas in California, Spain, and Australia that can collectively maintain contact as Earth rotates. Commands are uploaded typically once per day, and data is downloaded twice daily, though the telescope operates autonomously, executing pre-programmed observation sequences without real-time human intervention. Another advantage is that L2 keeps Webb out of Earth and Moon shadows. Hubble, in low Earth orbit, passes into Earth's shadow every 90 minutes, experiencing dramatic temperature swings that stress its components. Webb, at L2, maintains steady thermal conditions, always in sunlight, on the sun shield's hot side, while keeping its instruments perpetually cold. This thermal stability is crucial for maintaining the mirror alignment and ensuring consistent infrared performance. Webb's actual orbit at L2 is not a simple stationary position. Instead, it follows what's called a halo orbit, a large looping path around L2 that takes about 6 months to complete. This orbit keeps Webb from ever being eclipsed by Earth or Moon and avoids contamination from outgassing from Earth's upper atmosphere. The orbit does require periodic small thruster firings for station keeping, adjustments every 3 weeks or so to maintain position, but Webb launched with enough propellant for over 20 years of these maneuvers. The telescope itself is a marvel of engineering. Webb's primary mirror is more than 2.7 times larger in diameter than Hubble's, giving it over 7 times the light-gathering area. That might not sound like much of an improvement, but in astronomy, collecting area is crucial. A mirror twice as wide collects 4 times as much light. Webb's mirror, being 2.7 times wider, collects about 7.3 times as much light. When you're observing faint, distant objects, this extra light-gathering power makes an enormous difference. The mirror segments are made of beryllium, a lightweight metal that maintains its shape even at cryogenic temperatures. Each segment is coated with a microscopically thin layer of gold, which reflects infrared light more efficiently than the aluminum coating used on Hubble. The segments can be individually adjusted using tiny actuators on the back of each mirror, allowing the telescope to maintain perfect alignment even as temperatures change. Webb has 4 main scientific instruments, each designed for specific types of observations. The Near-Infrared Camera, NIR-CAM, observes wavelengths from 0.6 to 5 microns. The Near-Infrared Spectrograph, NIR-SPEC, obtains spectra, breaking light into its component wavelengths over a similar range. The Mid-Infrared Instrument, MIRE, observes from 5 to 28.5 microns, and the Fine Guidance Sensor, Near-Infrared Imager, and Slitless Spectrograph, FGS, NIRA-ESS, provides precise pointing control and additional imaging and spectroscopic capabilities. For observing the pillars of creation, NIR-CAM and MIRI are the key instruments. NIR-CAM, operating in the Isha-Naz, near-infrared, can see through much more dust than Hubble, revealing stars that are completely obscured in visible light. MIRI, sensitive to even longer wavelengths, shows the dust itself, revealing its temperature, distribution, and structure. The wavelength difference between what Hubble observes and what Webb observes is profound. Hubble's visible light observations range from about 0.38 to 0.75 microns. Hubble can extend into the near-infrared up to about 1.7 microns with certain instruments, and up to 2.5 microns with others. Webb starts at 0.6 microns, red visible light, and extends all the way to 28.5 microns, almost 50 times longer in wavelength. Webb's range covers wavelengths that Hubble simply cannot observe. Why does this matter so much for observing the pillars of creation? Because dust, which blocks visible light so effectively, becomes increasingly transparent at longer wavelengths. A dust grain that absorbs and scatters a blue photon, 0.45 microns, will likely let a mid-infrared photon, 10 microns, pass right through. The dust doesn't disappear. It's still there. But at infrared wavelengths, we can see through it, like looking through fog with infrared goggles. Moreover, the protostars embedded in the pillars emit most of their radiation in the infrared. A protostar in its earliest stages, still cold and accumulating mass, might have a temperature of only a few hundred Kelvin. At these temperatures, the peak of its thermal emission lies in the mid-infrared, around 5 to 20 microns. These stars are essentially invisible to Hubble, but glow brightly in Webb's view. The development of Webb was a decades-long process, fraught with technical challenges, budget overruns, and schedule delays. Originally conceived in the 1990s as the Next Generation Space Telescope, it was later renamed to honor James E. Webb, who led NASA during the Apollo program in the 1960s. The mission was initially projected to cost around $500 million and launch in 2007. By the time it actually launched in 2021, the total cost had grown to about $10 billion, and the launch had been delayed by 14 years. These delays and cost overruns were controversial, and at times, the mission's future was in doubt. But the scientific community remained committed to Webb, recognizing that its capabilities would revolutionize astronomy. There was simply no other way to achieve the combination of sensitivity, angular resolution, and wavelength coverage that Webb would provide. One of the concerns during Webb's development was its inability to be serviced. Hubble benefited immensely from 5 servicing missions, during which astronauts installed new instruments, replaced components, and performed repairs. Webb, at L2, is far beyond the reach of any crewed spacecraft currently available. Once launched, it would have to work perfectly, or the mission would fail. This necessitated exhaustive testing, with every component and system verified multiple times under conditions, simulating the space environment. The tension during deployment was palpable. Engineers spoke of 30 days of terror, each critical deployment step a potential single-point failure that could end the mission. The sunshield deployment alone involved 107 release mechanisms, 140 actuators, and over 400 pulleys. If any one of dozens of steps had failed, the sunshield might not have deployed correctly, leaving the telescope unable to cool sufficiently. Similar concerns existed for the mirror deployment, the secondary mirror boom, and numerous other systems. When Webb finally completed its deployment and began the months-long process of cooling down, aligning its mirrors, and calibrating its instruments, the astronomy community waited with cautious optimism. The first engineering images, released to demonstrate the telescope's focus and functionality, were promising. Then, on July 12, 2022, the first full-resolution science images were revealed to the public. They were spectacular, exceeding even the most optimistic expectations. Webb could see farther, deeper, and with more clarity than any infrared telescope before it. It captured the faint light of galaxies as they appeared just a few 100 million years after the Big Bang. Galaxies so distant, their light had been traveling through space for over 13 billion years. It revealed the detailed structure of planetary nebulae, the dying breaths of sun-like stars. It obtained spectra of exoplanet atmospheres, detecting water vapor, carbon dioxide, and other molecules on worlds orbiting distant suns. And in October 2022, Webb turned its infrared gaze toward a familiar target, the pillars of creation. The results, revealed to the public on October 19, 2022, were nothing short of stunning. The pillars we thought we knew, the structures captured so iconically by Hubble, were transformed. What had been dark became light. What had been hidden became revealed. And our understanding of star formation in this cosmic nursery deepened dramatically. The 2022 Webb Revelation. When NASA released James Webb's first image of the pillars of creation on October 19, 2022, the immediate response was one of awe mixed with disorientation. The pillars were recognizable, the same three towering structures Hubble had shown us, but they looked completely, almost impossibly different. Gone were the dark, imposing silhouettes against a glowing background. Instead, the pillars appeared almost translucent, their rust-colored gas and dust glowing from within, set against a deep, blue-black background, studded with thousands of stars. But here's what nobody expected. There were too many stars. Astronomers had modeled what Webb should see. They understood infrared astronomy. They knew Webb's sensitivity, knew how well infrared wavelengths penetrate dust. They predicted Webb would reveal stars that Hubble couldn't detect. Maybe a few dozen, perhaps 100. But when the data came in, when the images were processed, the count kept climbing. Dozens became hundreds. By some estimates, Webb revealed several times more forming stars than Hubble had identified. The pillars weren't just active. They were teeming with stellar birth, a nursery far more productive than visible light observations had ever suggested. This wasn't a minor discrepancy. It meant that all the previous estimates of star formation efficiency, all the models of how many stars the Eagle Nebula was producing, were significant underestimates. We'd been looking at these pillars for 27 years, studying them intensively, and we'd missed most of what was happening inside them. It was like thinking you were looking into a quiet room and then suddenly realizing it was hosting a party you couldn't see. The image was captured by Webb's near-infrared camera, an IR cam, using 6 different filters spanning wavelengths from 0.9 microns to 4.7 microns. Each filter isolated a different range of infrared wavelengths, and these were combined to create a false color image, where different infrared wavelengths were assigned visible colors our eyes could perceive. The shortest wavelengths appeared purple and blue in the final image. Middle wavelengths appeared yellow and orange, and the longest wavelengths appeared red. And then there were the protostars themselves. Scattered throughout the structures were bright red orbs, each one marking the location of a forming star. Some displayed prominent diffraction spikes, the characteristic 8-pointed star pattern created by light diffracting around the edges of Webb's hexagonal mirror segments and support structure. These weren't fully formed stars yet. They were infants, probably only a few 100,000 years old, still gathering mass from their surroundings, still growing. Their temperatures were cool by stellar standards, just a few hundred to perhaps 1,000 Kelvin, warm enough to glow in infrared light, but far too cool to emit significant visible light. Many of these protostars were surrounded by thick cocoons of dust, which absorbed the star's light and re-radiated it at even longer wavelengths. This is why they appeared as extended fuzzy red blobs rather than sharp points. The dust cocoon can extend for hundreds to thousands of astronomical units around the forming star, completely obscuring it in visible light, but glowing brightly in the infrared. Another striking feature of Webb's image is the glowing, almost lava-like structures visible along the edges of some of the pillars. These wavy, undulating lines of bright red and orange emission trace the edges of the pillars with an organic, flowing appearance. These aren't liquid lava, of course, but they do represent heat and motion. They're jets of material ejected by forming stars, supersonic outflows that slam into the surrounding gas and dust, heating and exciting it. When a star forms, it doesn't accrete all the material that falls toward it. Conservation of angular momentum, the same physics that makes a spinning ice skater spin faster when pulling in their arms, means that infalling material tends to form a rotating disk around the forming star. Some of this material is funneled toward the star's poles and ejected in powerful bipolar jets, streams of material shooting out at speeds that can reach hundreds of kilometers per second. These jets aren't visible directly in Webb's images, but their effects are. When a jet slams into the ambient gas and dust of the pillar, it creates a shock wave, compressing and heating the material. The heated gas emits infrared radiation, creating the glowing outlines and wavy structures we see. The wavy pattern arises from instabilities in the shock and from the jet's variable output. As the protostar goes through periods of more intense accretion alternating with quieter periods, the jet's strength varies, creating a pulse structure that shows up as waves and knots in the shocked gas. Some of these jets create bow shocks, structures that look like the wake of a boat moving through water. As the jet plows through the surrounding medium, it pushes material aside, creating a curved shock front shaped like a bow. These bow shocks can extend for significant distances from the protostar, sometimes reaching several light years in length. The pillars themselves, in Webb's view, appear semi-transparent. This is the key difference from Hubble's observations. In visible light, the dust is so opaque that we see only the surfaces. In near-infrared light, much of the dust becomes transparent, allowing us to see layers deeper into the structure. We can see stars that lie behind the pillars, their light filtering through the dusty veil. We can see structure within the pillars, variations in density and temperature that were invisible to Hubble. However, it's important to note that even Webb doesn't show us the deepest, densest cores of the pillars with complete clarity. The very center of the densest EGGs, where molecular hydrogen is packed most tightly, remains somewhat obscured even in the near-infrared. To probe those regions, we need even longer wavelengths, which is where Webb's mid-infrared instrument, MIRI, comes in. In November 2022, NASA released a second image of the Pillars of Creation, this time captured by MIRI at mid-infrared wavelengths from 7 to 18 microns. This image was dramatically different from both Hubble's visible light view and Webb's NIRCam near-infrared view. The pillars appeared as ghostly, smoky structures in shades of gray and brown-gray, almost ethereal against a dark background tinged with deep reds and oranges. In MIRI's view, thousands of the stars visible in the NIRCam image disappeared. This isn't because MIRI is less sensitive, but because stars, even young ones, are relatively hot objects that emit most of their light at shorter wavelengths. In the mid-infrared, stars appear much fainter. What MIRI excels at revealing is dust, which is warmed by stellar radiation and re-emits that energy in the mid-infrared. The structures visible in the MIRI image trace the distribution and temperature of the dust. The densest regions, where dust is packed most tightly, appear as the darkest areas, opaque even in the mid-infrared. The outer layers, where dust is being heated by radiation from nearby stars, glow in rust and orange hues. The overall appearance is haunting, almost spectral, like cosmic smoke frozen in time. Embedded within these smoky structures, MIRI revealed something Hubble never could: the very youngest protostars, stars so deeply buried that even NIRCam couldn't see them clearly. These appear as tiny glowing dots of red, almost like the eyes of cosmic jack-o'-lanterns peeking out from the darkness. These are stars that have barely begun to form, objects so young and so cold that they emit almost no light at near-infrared wavelengths, but glow faintly in the mid-infrared. The combination of NIRCam and MIRI observations, one showing the near-infrared and the other the mid-infrared, provides a complementary view of the star formation process. NIRCam shows us slightly older protostars that have warmed up enough to emit significant near-infrared radiation. MIRI shows us the youngest, coldest protostars that are just beginning to glow. Together, they reveal a population of forming stars at different stages, giving us a more complete census of star formation in the pillars. Astronomers also created a composite image combining NIRCam and MIRI data, blending near and mid-infrared observations into a single view. In this composite, the pillars appear in shades of blue, purple, and orange, with myriad stars scattered throughout the scene. The densest regions show up in deep blue and purple, representing the coolest dust. The outer layers, warmed by stellar radiation, appear in orange and red, and the stars, visible primarily in the near-infrared NIRCam data, sprinkle the image with points of white and yellow light. One of the most significant scientific results from Webb's observations is the updated census of protostars in the pillars of creation. While Hubble identified about 50 EGGs, Webb revealed many more protostars. Some estimates suggest Webb detected several times as many forming stars as Hubble could identify. This is crucial for understanding the overall star formation efficiency in this region. Star formation efficiency is the fraction of a molecular cloud's mass that actually forms stars before the cloud is dispersed. In the pillars of creation, photoevaporation from nearby massive stars is actively dispersing the cloud, cutting off the supply of material to forming stars and eventually destroying the pillars entirely. By counting how many stars form and estimating their masses, astronomers can determine what fraction of the original cloud's mass went into stars before photoevaporation ended the process. Webb's observations suggest star formation in the pillars is actually more active than visible light. Observations indicated many of the protostars Webb detected were completely invisible to Hubble, meaning previous estimates of the star formation rate and efficiency were underestimates. This has implications for understanding star formation in similar regions throughout the galaxy and the universe. Another important finding relates to the ages and masses of the protostars. By measuring their infrared colors and brightness, astronomers can estimate how old they are and how massive they're likely to become. Initial analysis suggests most of the protostars Webb detected are very young, less than 1 million years old, and range in mass from less than a solar mass up to several solar masses. Interestingly, the most massive forming stars don't seem to be in the densest EGGs. They're more commonly found near the edges of the pillars, or in regions where the pillars are actively being eroded. This suggests that the environment matters. The most massive stars may form in regions where material is being actively stripped away, exposing them early, while stars forming in the protected cores of the EGGs may have their growth limited by the eventual destruction of their surroundings. Webb's observations also revealed the complex three-dimensional structure of the pillars more clearly than before. By observing in infrared wavelengths that penetrate the dust, Webb could see features at different depths within the structures. Some protostars are clearly near the front surfaces of the pillars, from our viewing perspective, while others are embedded more deeply, partly obscured by foreground dust. This layering helps astronomers build a three-dimensional model of the region, understanding not just what we see projected on the sky, but how the structures extend in depth. The jets and outflows visible in Webb's images also provide information about the star formation process. The orientation of these jets can indicate the rotation axis of the protostar and its surrounding disk. The strength and extent of the outflows tell us about the accretion rate and the star's current state of formation. By studying multiple protostars at different stages, astronomers can piece together a timeline of how these jets evolve as a star grows. One particularly intriguing feature visible near the top of the left pillar in Webb's NIRCam image is a diagonal jet of ejected material. This jet, cutting across the pillar at an angle, is evidence of a forming star, even though the star itself isn't visible at that location. The jet is present, glowing in infrared light, but the star producing it is still so deeply embedded that even Webb can't see it directly. We're seeing the star's influence, the material it's ejecting, but not the star itself. It's like seeing a ship's wake, but not the ship. Another feature that becomes clear in Webb's images is the fine structure of the pillar's surfaces. The edges aren't smooth, but highly convoluted, with small finger-like projections, knots, and streamers. This fine structure is sculpted by photoevaporation, but the details depend on the local density and composition of the gas. Regions that are slightly denser erode more slowly, forming projections. Regions that are less dense erode faster, creating depressions and hollows. This complex morphology has implications for understanding how photoevaporation works on small scales. It's not a uniform process, but is sensitive to small variations in the cloud's initial structure. This means that the final population of stars that forms, their masses and locations, is influenced not just by the large-scale environment, but by small-scale structure in the original molecular cloud. Perhaps most striking about Webb's observations is the sheer aesthetic beauty of the images. While Hubble's pillars were dramatic and imposing, Webb's pillars are warm and inviting, glowing with an internal light. The rust and orange hues, the delicate tracery of jets and outflows, the thousands of stars peeking through the dust, all combine to create images that are, in their own way, as iconic as Hubble's original. But unlike Hubble's view, which showed us mystery and darkness, Webb's view shows us illumination and revelation. We're not looking at opaque monuments anymore. We're looking inside cosmic nurseries, witnessing the birth of stars in unprecedented detail. What was hidden is now revealed. What was mysterious is now, if not fully understood, at least visible and measurable. The scientific value of these observations will take years to fully exploit. Astronomers will analyze the data in detail, measuring the properties of individual protostars, mapping the distribution of gas and dust, studying the dynamics of jets and outflows, and building detailed models of how star formation proceeds in this environment. Each protostar is a data point, each jet a constraint on models, each structure a clue to the physics governing the process. But beyond the science, Webb's pillars of creation, images serve another purpose. They remind us that the universe is not a cold, lifeless void, but a place of constant change and creation. They show us that even in the darkness between stars, life, in the form of new stars, is being born. They demonstrate that when we change our perspective, when we look at the same object in a different way, we discover new truths that were there all along, waiting to be revealed. Side by side, two perspectives. The true power of having both Hubble and James Webb observations of the pillars of creation becomes clear when we place the images side by side and examine what each reveals. They're not simply two different pictures of the same object. They're complementary views that together tell a richer, more complete story than either could alone. Start with the overall appearance. Hubble's visible light image shows the pillars as dark, imposing columns rising against a glowing emerald and amber background. The pillars themselves are nearly black in their densest regions, with edges illuminated in golden light. The background, though not empty, is relatively sparse, with perhaps a few dozen stars visible. The overall impression is one of towering monumentality, structures that could have been carved by titans from primordial stone. Webb's near-infrared image shows the same three pillars, but they're transformed. They glow from within in shades of rust, orange, and brown-gray. They're translucent rather than opaque, with variations in brightness and color revealing internal structure. The background is crowded with stars, thousands of them, ranging from tiny dots to brighter stellar points. The overall impression is one of bustling activity, a stellar nursery in full operation, with stars being born throughout the structure and peeking out from behind every dusty veil. The differences arise directly from the wavelengths each telescope observes. Visible light, which Hubble detects, interacts strongly with dust grains. A dust grain, typically smaller than a micron in size, is roughly the same size as the wavelength of visible light, 0.4 to 0.7 microns. When light of a wavelength similar to an object's size strikes that object, there's a high probability of interaction, either absorption or scattering. This is why dust clouds appear dark and opaque in visible light. Infrared light, especially at wavelengths longer than a few microns, is much larger than typical dust grains. When infrared light encounters a dust grain, there's a lower probability of interaction. Much of the infrared light passes right by the grain without being absorbed or scattered. This is why infrared wavelengths can penetrate dust clouds that are completely opaque to visible light. It's analogous to the difference between a basketball, representing an infrared photon, encountering a marble, representing a dust grain, versus a marble encountering another marble of similar size. The stars visible in each image also differ. In Hubble's view, we see primarily hot, blue stars from the NGC 6611 cluster, stars with surface temperatures of tens of thousands of Kelvin. These stars emit most of their light in ultraviolet and blue, visible wavelengths. They're bright in visible light, but not particularly prominent in infrared. In Webb's view, we see a broader population. The hot blue stars are still there, but appear less dominant. We also see cooler stars, red dwarfs, and older stars that emit more of their light in the infrared. And crucially, we see the protostars, objects that aren't yet stars in the traditional sense, but glow primarily in infrared wavelengths due to their low temperatures. The distribution of protostars reveals the active star formation happening throughout the pillars. In Hubble's images, we could infer where stars were forming by looking at the EGGs, but we couldn't see the stars themselves. Webb's images make the star formation explicit, showing us dozens of glowing red orbs marking sites of stellar birth. The jets and outflows provide another point of comparison. In Hubble's visible light images, some evidence of outflows is visible as faint streamers of ionized gas. But the jets themselves, moving through neutral molecular gas, don't produce much visible light emission. In Webb's infrared images, the jets light up prominently, traced by the shock-heated gas along their edges. The wavy, lava-like structures Webb reveals are essentially invisible to Hubble, hidden at wavelengths Hubble can't observe. The background also tells different stories. Hubble's view shows the glowing ionized hydrogen surrounding the pillars, the hot gas heated by ultraviolet radiation from nearby stars. This gas emits primarily in visible wavelengths, particularly in emission lines like H-alpha. Webb's view shows the same region, but reveals less of this ionized gas, which doesn't emit strongly in infrared, and more of the colder neutral gas and dust, which radiates in the infrared. Interestingly, both images show relatively little in the way of distant galaxies in the background. Normally, deep space images reveal numerous galaxies scattered across the field, but the pillars of creation lie within the dense portion of our Milky Way's disk. The interstellar medium, the gas and dust between stars in our galaxy, creates a veil that blocks our view of the distant universe. It's like trying to look through fog. Objects beyond the fog, even bright ones, are obscured or invisible. This is true for both visible and infrared wavelengths, though infrared can penetrate somewhat farther through the galactic dust. When viewing the images side by side, one can also appreciate the different textures each wavelength reveals. Hubble's visible light image has a painterly quality, with smooth gradients of light and dark, subtle variations in color, and relatively clean edges. Webb's infrared image has a more structured, almost fibrous quality, with intricate detail in the dust distribution, variations in brightness on small scales, and a generally more complex appearance. This difference reflects what each wavelength is sensitive to. Visible light shows us ionized gas and scattered starlight, processes that produce relatively smooth distributions. Infrared light shows us the dust directly, and the thermal emission from protostars, revealing more of the fine-scale structure of the cloud. Astronomers have also created composite images, blending Hubble and Webb data, attempting to show both perspectives in a single view. These composites typically assign Hubble's visible light data to blue and green colors, and Webb's infrared data to orange and red. The result is a riot of color, with pillars that glow in orange and brown from Webb's infrared view, while still showing the blue-green ionized gas from Hubble's visible light view. These composites are beautiful, but can be challenging to interpret, as they're mixing information from very different physical processes. A more scientifically useful approach is to view the images in sequence, switching from Hubble to Webb and back, allowing the viewer's brain to process the differences. NASA has created animations that do exactly this, morphing between Hubble's view and Webb's view, making the transformation dramatic and immediate. When you see the pillars shift from dark to light, from opaque to transparent, from mysterious to revealed, the complementary nature of the two perspectives becomes viscerally clear. One of the questions often asked is whether one view is more real than the other. The answer is that both are real, but both are also false, in the sense that neither shows what a human eye would see if somehow transported to the location of the pillars. Human vision is limited to visible wavelengths, roughly 0.4 to 0.7 microns. If you could look at the pillars with your naked eyes, ignoring the lethality of being in space, you'd see something more like Hubble's visible light image, though without the false colors added in processing. But what we would see is not necessarily the most scientifically valuable view. Our eyes evolved to see visible light because that's the light available on Earth's surface, filtered through our atmosphere. In space, restricting ourselves to visible light would mean missing most of the information available. By observing in wavelengths our eyes can't see, we learn things that visible light can't tell us. This is a general principle in modern astronomy. We observe the universe across the entire electromagnetic spectrum, from gamma rays with wavelengths smaller than an atom, to radio waves with wavelengths longer than a person is tall. Each wavelength range reveals different physical processes, different temperatures, different densities, different phenomena. The visible spectrum, though special to us as biological beings, is just one small slice of the full picture. The complementarity of Hubble and Webb extends beyond just the pillars of creation. Throughout astronomy, these two telescopes work together, each contributing their unique perspectives. Hubble can detect shorter wavelengths, including ultraviolet light that Webb can't observe, revealing the hottest objects and the most energetic processes. Webb detects longer wavelengths, including mid-infrared light that Hubble can't observe, revealing the coldest objects and the most dust-obscured regions. For studying distant galaxies, Hubble shows us their stellar populations, the stars that make up the galaxy, and their colors and distributions. Webb shows us the gas and dust, the raw material from which stars form, and can detect galaxies so far away that their light has been redshifted from ultraviolet and visible into infrared. For studying exoplanet atmospheres, Hubble can detect certain molecules through their visible and near-infrared absorption, while Webb's mid-infrared sensitivity allows detection of molecules like carbon dioxide and methane. For studying planetary nebula, Hubble reveals the ionized gas glowing in emission lines, while Webb shows the dust ejected by the dying star. In the case of the pillars of creation, the combination is particularly powerful because star formation involves both hot and cold components. The massive stars whose ultraviolet radiation is photoevaporating the pillars are hot, tens of thousands of Kelvin, emitting primarily in ultraviolet and visible wavelengths. The forming stars buried within the pillars are cold, hundreds of Kelvin, emitting primarily in infrared. To understand the full process, how hot stars shape the environment and regulate the formation of the next generation, we need both perspectives. This complementarity also highlights an important point about scientific progress. Science doesn't typically advance through sudden revolutions where old knowledge is overturned. More often, it advances through refinement, through adding new data and new perspectives that deepen our understanding. Hubble didn't solve the mystery of the pillars of creation. It revealed structures and posed questions. Webb didn't replace Hubble's observations. It added another layer, answering some of Hubble's questions while posing new ones of its own. The next step would be additional observations at other wavelengths. X-ray observations with Chandra have detected young stars throughout the Eagle Nebula, including around the pillars. Radio observations with ALMA, the Atacama Large Millimeter-Submillimeter Array, can map the cold molecular gas with exquisite detail, showing how the gas moves and where it's densest. Ultraviolet observations with Hubble, which Webb can't do, reveal the hot ionized gas and the most massive stars. Each new wavelength adds another piece to the puzzle. But even with all these observations across the spectrum, our understanding remains incomplete. We see snapshots, frozen moments in a process that unfolds over millions of years. We can't watch a single protostar through its entire formation process. Can't see a pillar erode in real time. We build understanding by looking at many objects at different stages, using our spatial senses to reconstruct temporal evolution, and by comparing observations with theoretical models. This is the power of having two telescopes as capable as Hubble and Webb operating simultaneously. They double-team cosmic mysteries, each bringing their own strengths, each revealing aspects the other cannot. Together, they provide a richness of data, a breadth of perspective that single telescope astronomy could never achieve. The science of star birth. To truly understand what we're seeing in the pillars of creation, whether through Hubble's or Webb's eyes, we need to delve into the physics of star formation itself. How do stars actually form? What transforms a cloud of cold gas into a glowing ball of nuclear fusion? And what role does the environment play in determining what kinds of stars are born? Star formation begins, with gravity. In the cold depths of molecular clouds, where temperatures hover just a few degrees above absolute zero, gas exists in a delicate balance. Thermal pressure, the random motion of molecules, pushes outward, resisting compression. But gravity, the mutual attraction of every molecule for every other molecule, pulls inward. For most of the cloud, these forces balance. The cloud is stable, neither collapsing nor expanding, existing in equilibrium that can persist for millions or tens of millions of years. But if something disturbs this balance, if a region becomes slightly denser than its surroundings, gravity can begin to win. The denser region pulls in more material, becoming denser still, which increases its gravitational pull, pulling in even more material in a runaway process called gravitational collapse. Once collapse begins, it's difficult to stop. What can trigger collapse? Several mechanisms are possible. A shockwave from a nearby supernova can compress the cloud, pushing it past the threshold of gravitational instability. The collision of two molecular clouds can create dense regions where they meet. The passage of a spiral density wave through the galactic disk can compress gas, triggering widespread star formation. Or turbulent motions within the cloud itself, random compressions, and rarefactions can create dense pockets that begin to collapse. In the pillars of creation, the trigger might have been the formation of the NGC 6611 cluster itself. When the first generation of massive stars formed in this region, their intense radiation and stellar winds swept away less dense gas, compressing what remained into the pillars and other dense structures we see today. This compression might have pushed the pillars over the edge into gravitational collapse, triggering the current episode of star formation. As a region collapses, several things happen. The center becomes denser and denser, eventually forming what's called a protostellar core, a condensed region that will become a star. Material continues to fall onto this core, increasing its mass. As matter falls inward, gravitational potential energy converts to kinetic energy, and then to heat, warming the core. The collapsing region spins, conserving angular momentum, which causes infalling material to form a rotating disk around the core. And jets of material are ejected from the star's poles, carrying away angular momentum and allowing more material to accrete. The disk is crucial. Without it, the conservation of angular momentum would prevent most of the cloud from reaching the star. Material far from the rotation axis has too much angular momentum to fall directly onto the star. It must first shed some of that angular momentum, which happens through processes in the disk. Magnetic fields threading through the disk can transport angular momentum outward, allowing material to spiral inward. Gravitational interactions within the disk, creating spiral density patterns, can also redistribute angular momentum, and the jets remove angular momentum from the system, helping material accrete. As the protostellar core grows, it heats up. Initially, the temperature is just a few degrees Kelvin, barely above absolute zero. But as material falls in and is compressed by gravity, the temperature rises. By the time a protostar has accumulated a significant fraction of a solar mass, its core temperature might reach a few hundred Kelvin, warm enough to begin glowing in the infrared. This is the stage where Webb can start to detect these objects, as they've warmed enough to emit detectable mid-infrared radiation. The protostar continues to accumulate mass for hundreds of thousands to a few million years. During this time, it's surrounded by an envelope of gas and dust, the remains of its natal cloud, which obscures it from view at visible wavelengths. The envelope slowly dissipates as material falls onto the star or is driven away by the stellar winds and jets. Eventually, the envelope becomes thin enough that visible light can escape, and we see a visible star surrounded by a disk. But the star isn't yet a true main sequence star. Its core, though hot, isn't yet hot enough for sustained hydrogen fusion. For hydrogen fusion to occur, the core temperature must reach about 10 million Kelvin. At that temperature, hydrogen nuclei, protons, have enough kinetic energy to overcome their mutual electrostatic repulsion and fuse together, releasing energy through the conversion of mass to energy via Einstein's equation EXmc2. To reach such temperatures requires immense gravitational compression. The protostar must accumulate enough mass that its own weight compresses the core to the necessary density and temperature. For a star like the Sun, this takes roughly 50 million years from the beginning of collapse. More massive stars reach fusion temperatures more quickly. Less massive stars take longer, and the least massive objects, with masses below about 0.08 solar masses, about 80 times Jupiter's mass, never reach fusion temperatures at all. remaining as brown dwarfs, failed stars that glow faintly from residual heat but never ignite. This is where photoevaporation enters the story. The protostars forming in the pillars of creation are not forming in isolation. They're forming in the shadow of the NGC 6611 cluster, a group of massive hot stars that formed earlier from the same molecular cloud. These massive stars, some with masses 20 or 30 times that of the Sun, emit intense ultraviolet radiation, photons energetic enough to ionize hydrogen. When this ultraviolet radiation strikes a molecular cloud, it heats and ionizes the surface layers, causing them to expand and flow away. This is photoevaporation, and it's a double-edged sword. On one hand, it can trigger star formation by compressing the cloud. On the other hand, it can limit or even prevent star formation by dispersing the cloud before gravity can pull it together. For the protostars in the EGGs, photoevaporation is a race against time. Can they accumulate enough mass to become viable stars before photoevaporation disperses their natal clouds? The answer depends on several factors: how dense their original cocoon was, how fast they're accreting material, and how intense the ultraviolet radiation field is. The EGGs themselves are the densest regions, massive enough that photoevaporation erodes them relatively slowly. But even these structures are temporary. Models suggest they might survive for 1 million years or so before being completely dispersed. Some of the protostars within will complete their formation in that time, emerging as fully formed stars. Others may be caught mid-formation when their clouds are dispersed, resulting in stars whose masses are frozen at whatever they had accumulated, unable to grow larger because their supply of material has been cut off. This has profound implications. In an isolated molecular cloud, far from massive stars, forming stars can continue accreting for many millions of years, potentially reaching very large masses. But in regions like the pillars of creation, where photoevaporation is active, star masses are limited. This might explain why there are so many low to intermediate mass stars in the galaxy. Photoevaporation and other feedback processes from massive stars may regulate star formation, limiting how massive stars can grow and determining the overall distribution of stellar masses. The jets and outflows we see in Webb's images are another crucial part of the star formation process. These jets can extend for light years, carrying away mass and momentum from the forming star. When they slam into the surrounding cloud, they create shockwaves that heat and compress the gas, possibly triggering additional star formation in their vicinity. This is an example of positive feedback. Star formation, driving more star formation. But there's also negative feedback. The jets, along with stellar winds and radiation pressure, drive material away from the forming star. This material was potentially fuel for further growth, but instead, it's ejected from the system. Over time, this negative feedback, combined with photoevaporation, disperses the cloud, ending star formation in that region. The interplay between positive and negative feedback, between processes that enhance star formation and those that suppress it, determines how efficiently a molecular cloud converts its mass into stars. Observations suggest star formation is relatively inefficient. Only about 1 to 10% of a molecular cloud's mass typically ends up in stars before the cloud is dispersed. The rest is blown away by stellar winds, heated and ionized by radiation, or simply disperses as the cloud's turbulent motions eventually overwhelm its self-gravity. This inefficiency is actually crucial for the structure of galaxies. If star formation were highly efficient, molecular clouds would convert almost all their mass into stars very quickly, leading to bursts of intense star formation, followed by long quiescent periods. Instead, the low efficiency of star formation spreads the process out over time, maintaining a relatively steady rate of star formation that sustains galactic structure. The chemical composition of forming stars also matters. The gas in the pillars of creation contains not just hydrogen and helium, but heavier elements, metals, in astronomical terminology. These metals, while comprising only about 1 to 2% of the mass, play several important roles. Metal atoms and molecules are efficient at radiating away heat, helping the gas cool and collapse. Dust grains, made of metals and other heavy elements, shield the interior of clouds from destructive radiation and provide surfaces where molecules like H2 can form. And metals will eventually be incorporated into planets once the star finishes forming. The presence of these metals tells us that earlier generations of stars lived and died in this region. Those stars forged elements heavier than helium in their cores through nuclear fusion and distributed those elements into space through supernova explosions and stellar winds. The stars forming now in the pillars are not first-generation stars, but third or fourth or perhaps even later generation stars, enriched by the products of earlier stellar evolution. When one of these new stars eventually dies, it too will return material to the interstellar medium, further enriching it. If the star is massive enough, it will explode as a supernova, creating even heavier elements in the explosion and distributing them across the galaxy. If it's less massive, like the Sun, it will eventually shed its outer layers as a planetary nebula, enriching the surrounding space with the products of helium fusion synthesized during the star's red giant phase. This cycle of stellar birth, life, and death has been ongoing since the first stars formed roughly 13 billion years ago. Each new generation of stars is slightly more metal-rich than the last, slowly changing the chemical composition of the galaxy. By studying the metal content of stars and gas clouds, astronomers can trace this chemical evolution, understanding how galaxies have changed over cosmic time. The pillars of creation represent just one snapshot of this ongoing cycle. The molecular cloud from which they formed accumulated over millions of years, gathering gas expelled from earlier stars. The first generation of stars to form, the NGC 6611 cluster, lived quickly and violently, emitting intense radiation that sculpted the remaining cloud into the pillars we see. Now, a second generation is forming within those pillars, and in a few million years, those stars will emerge, shining as the next generation of the cluster. Eventually, the pillars will be completely dispersed, leaving behind only the stars they birthed, and those stars will continue to evolve, some living for billions of years, others dying, in mere millions, each contributing in their own way to the ongoing story of the galaxy. Hidden stars emerge. One of James Webb's most significant contributions to our understanding of the pillars of creation is the sheer number of previously hidden stars it revealed. But understanding what we're seeing in those bright red orbs scattered throughout Webb's images requires delving into the details of protostellar evolution and how astronomers classify these objects. A protostar is not a single well-defined stage, but rather a continuous evolutionary process. Astronomers typically divide this process into several classes based on the spectral energy distribution, essentially the relative brightness at different wavelengths, which changes as the protostar evolves. Class 0 protostars are the youngest and most embedded. They've just begun to form, with most of their mass still in a surrounding envelope rather than in the central object. They're completely invisible at visible and even near-infrared wavelengths, detectable only at far-infrared and radio wavelengths. Webb's MIRI instrument, operating in the mid-infrared, can detect these objects, seeing them as faint red glows deep within the densest cores. Class 1 protostars are somewhat more evolved. They've accumulated more mass in the central object, though a substantial envelope still surrounds them. They emit more of their energy at shorter wavelengths, becoming bright in the mid-infrared and detectable in the near-infrared. Many of the bright red orbs in Webb's NIRCam images are likely Class 1 protostars, objects warm enough and clear enough of surrounding material to glow brightly at wavelengths of a few microns. Class 2 objects are even more evolved. The envelope has largely dissipated, revealing a central star surrounded by a disk of material. These are T Tauri stars, named after the prototype T Tauri in the constellation Taurus. They're visible at optical wavelengths and are clearly stellar in nature, though still surrounded by disks from which planets might form. Some of the stars visible in both Hubble's and Webb's images of the pillars might be Class 2 objects, stars that have emerged from their cocoons but are still in their infancy. Class 3 objects are pre-main sequence stars with little or no remaining disk material. They're almost mature stars, approaching the main sequence where they'll spend most of their lives burning hydrogen in their cores. From a distance, they look like regular stars, though detailed observations can reveal they're still settling down, their luminosities and temperatures still adjusting toward their final main sequence values. In Webb's images of the pillars, we're primarily seeing Class 0 and Class 1 objects, the youngest protostars that are still deeply embedded or recently emerged from their natal clouds. The red color in the false color images indicates they're cool by stellar standards, with temperatures of perhaps a few hundred to 1,000 Kelvin, emitting primarily at infrared wavelengths between 3 and 10 microns. But these aren't uniform objects. Each protostar is unique, with its own mass, its own accretion rate, its own disk properties, its own jet characteristics. Some are accreting material rapidly, growing quickly as material streams onto them from the surrounding envelope. Others are accreting slowly, having consumed most of the easily accessible material in their vicinity. Some have strong jets, visible as the bright outflows in Webb's images. Others have weaker, or perhaps no jets, their outflow activity having subsided or being oriented such that we don't see it clearly. The distribution of protostars throughout the pillars is also informative. They're not uniformly distributed, but are concentrated in certain regions, along the edges of the pillars, particularly near the tips, and within the EGGs. This clustering suggests that star formation is triggered by the structure of the cloud itself. The densest regions, where gravity is strongest, collapse first. The tips of the pillars, where material is funneled by the pillar geometry, become sites of enhanced density and thus enhanced star formation. Astronomers can estimate the masses of these protostars by measuring their infrared luminosity and modeling their spectral energy distributions. A more luminous protostar, emitting more infrared light, is likely either more massive or accreting material more rapidly, or both. By combining infrared measurements with observations at other wavelengths and comparing with theoretical models, rough mass estimates can be derived. Initial analysis of Webb's observations suggests the protostars in the pillars range in mass from perhaps 0.1 solar masses, low-mass stars that will end up as red dwarfs, up to several solar masses, intermediate mass stars that will end up similar to or somewhat more massive than the Sun. There don't appear to be any very massive protostars. Stars destined to be O or B spectral types, forming in the pillars currently. Those stars likely formed earlier, part of the NGC 6611 cluster, whose radiation is now shaping the environment. The ages of these protostars can be estimated by comparing their observed properties with evolutionary models. Most appear to be less than 1 million years old, with many possibly only a few 100,000 years old. On a cosmic timescale, they're newborns, having just recently begun their journey toward becoming main sequence stars. One interesting question is how these protostars will evolve given their environment. Will they have time to accumulate enough mass to become viable hydrogen-burning stars? Will photoevaporation cut off their supply of material before they reach the main sequence? For the more massive protostars, those already near a solar mass, the answer is likely yes. They've accumulated enough mass that even if photoevaporation disperses their remaining envelope, they'll complete their evolution to the main sequence. For the lowest mass objects, the situation is less clear. If a protostar has only accumulated 0.1 or 0.2 solar masses when photoevaporation disperses its cloud, will it manage to gather enough additional material to reach the 0.08 solar mass threshold for hydrogen fusion? Or will it remain a brown dwarf, a substellar object that glows from residual heat but never ignites fusion? Some of the faintest red dots in Webb's images might be such objects, protostars that may or may not make it to full stellar status. The jets visible in Webb's images provide another window into protostellar properties. The presence of a strong jet indicates active accretion. Material falling onto the protostar releases gravitational potential energy, heating the immediate surroundings and driving outflows. By measuring the extent and brightness of these jets, astronomers can estimate the accretion rate, how much mass per year is falling onto the star. Typical values for low to intermediate mass protostars range from about 10 to 7 to 10 to 5 solar masses per year, meaning it takes hundreds of thousands to millions of years to build up a solar mass of material. The jets also carry important information about the protostar's magnetic field. Jets are thought to be magnetically driven, with magnetic field lines threading through the disk and funneling material toward the poles where it's ejected at high velocities. The structure of the jet, its degree of collimation, and its variability all depend on the magnetic field, geometry, and strength. By studying jets in detail, astronomers can probe magnetic fields in star-forming regions, fields that are otherwise difficult to measure. One particularly valuable aspect of Webb's observations is the ability to detect variability. Protostars are not constant in their brightness. They flicker and vary on timescales from days to years, driven by variations in accretion rate, by obscuration from disk material passing in front of the star, or by changes in the jet activity. By observing the same region multiple times, Webb could detect such variations, providing insights into the dynamic processes at work. Future observations with Webb might also include spectroscopy, breaking the infrared light from these protostars into its component wavelengths. Spectroscopy reveals the chemical composition, temperature, density, and motion of the gas. By obtaining spectra of the protostars and their surrounding material, astronomers can measure how fast gas is falling onto the star, whether the disk is rotating as expected, and what molecules are present in the circumstellar environment. Molecules like water, carbon monoxide, and organic compounds have been detected in protostellar disks using spectroscopy, hinting at the chemical complexity that might eventually lead to planet formation and perhaps life. Webb has also revealed that star formation in the pillars is an ongoing process, not something that happened once in the past. The range of protostellar ages and stages suggests a continuous or perhaps episodic process of star formation extending over at least 1 million years. New protostars continue to form even as older ones emerge from their cocoons and begin their lives as visible stars. This finding has implications for understanding star formation more broadly. In some models, star formation in a molecular cloud happens in a single, brief burst, with all the stars forming roughly simultaneously. But observations of regions like the pillars suggest a more extended process, with star formation continuing for several million years before the cloud is finally dispersed. The spatial distribution of protostars might also reveal how star formation propagates through a cloud. If the earliest stars form in one region and their feedback, radiation, winds, jets, compresses nearby gas, triggering formation of the next generation, we might see an age gradient, with the oldest stars in one location and younger protostars progressively farther away. Some observations of star-forming regions suggest such propagation, though it's not always easy to detect. Another intriguing possibility is that some of the protostars we see are in binary or multiple systems. Many stars form not in isolation, but in pairs or small groups. By measuring the positions and motions of protostars precisely, astronomers can identify binaries, multiple systems where two or more protostars orbit each other. Webb's sharp infrared images can resolve objects separated by just a few hundred astronomical units, allowing detection of binary protostars that would appear as single objects to less capable instruments. Binary star formation is still not fully understood. Do binaries form from the fragmentation of a single collapsing core, or do they form from separate cores that later interact gravitationally and become bound? Observations of young protostars at different stages can help answer these questions. If we see binaries at very early stages, it suggests fragmentation of the original core. If binaries are more common among older protostars, it might suggest capture or gravitational interaction. The protostars in the pillars, once they emerge from their cocoons and become visible stars, will likely remain gravitationally bound to each other for at least some time, forming a small cluster or association. Over millions of years, this cluster will gradually disperse as interactions between stars and with the galactic tidal field eject members. Most stars are thought to form in clusters, and our own sun was likely born in a cluster similar to the one now forming in the pillars of creation. By studying these protostars, we're studying not just the formation of individual stars, but the formation of stellar systems, perhaps entire planetary systems. The disks surrounding these protostars are the raw material from which planets will form. Over the next few million years, dust grains in these disks will stick together, forming larger and larger bodies. Pebbles, then boulders, then planetesimals, and finally planets. Some disks might form Earth-like rocky planets. Others might form gas giants like Jupiter. Still, others might produce exotic systems unlike anything in our solar system. Webb might even be able to detect the earliest stages of planet formation in these disks. At mid-infrared wavelengths, MIRI can observe the thermal emission from dust in disks, mapping their temperature and distribution. Gaps and rings in disks, which might indicate the presence of forming planets, could be detected. Spectroscopy could reveal the chemical composition of the disk material, telling us what ingredients are available for planet formation. Each protostar web reveals in the pillars of creation represents not just a forming star, but a potential planetary system, a future solar system where planets might orbit, where moons might form, where perhaps someday, billions of years from now, life might arise. The bright red dots scattered throughout Webb's images are not just data points in an astronomical study. They're the beginnings of worlds, cosmic seeds from which entire systems will grow. The broader story. The pillars of creation, while extraordinary in their own right, are part of a much larger story about star formation, galactic evolution, and the cycle of matter through the universe. To truly appreciate what we're seeing in these images, we need to place them in the broader context of cosmic structure and history. Star formation is not a rare or unusual phenomenon. It's happening constantly throughout the universe, in galaxies near and far. Across the Milky Way, stars are forming in hundreds of molecular clouds, similar to the Eagle Nebula. Some of these regions, like the Orion Nebula at about 1,350 light-years distance, are closer and provide even more detailed views of the star formation process. Others are more distant, but potentially more active, forming stars at higher rates or forming more massive stars. Throughout the universe, particularly in young galaxies or galaxies experiencing bursts of star formation, this process is ongoing at much higher rates than in the Milky Way. Starburst galaxies, driven by galaxy interactions or mergers, can form stars at rates hundreds or thousands of times higher than our galaxy. In these extreme environments, entire molecular clouds are compressed and triggered into rapid star formation, creating clusters of thousands or millions of stars in relatively small volumes of space. But despite this ubiquity, each star-forming region is unique. The pillars of creation have their particular characteristics. the specific density and temperature of the gas, the specific intensity and spectrum of the radiation field from NGC 6611, the specific geometry that creates the pillar structures. Star formation in other regions proceeds under different conditions, producing different structures and potentially different populations of stars. One of the key questions in star formation research is what determines the initial mass function, the distribution of stellar masses produced when a cloud collapses. Observations show that low-mass stars are far more common than high-mass stars. For every star with 10 times the Sun's mass, there might be thousands of stars with masses less than the Sun. This distribution seems to be relatively universal, similar in different star-forming regions, and even in different galaxies. But why? What sets this distribution? Is it determined by the properties of the molecular cloud, or by the physics of the collapse process, or by feedback from forming stars? Observations of regions like the pillars, where we can see many protostars at different masses and different stages, provide crucial data for answering these questions. The pillars of creation also remind us of the interconnectedness of stellar generations. The massive stars in NGC 6611 that are photoevaporating the pillars are themselves products of earlier star formation in this region. They formed from the same molecular cloud that now feeds the pillars just a few million years earlier. Their short lifetimes, massive stars live only a few million to tens of millions of years, mean they were born, lived, and are now shaping the next generation in the cosmological blink of an eye. In another few million years, these massive stars will die, exploding as supernovae that will distribute their processed material across the region. The shock waves from these explosions might trigger further star formation in nearby clouds, compressing them and pushing them into collapse. Or they might disrupt and disperse clouds, ending star formation. The balance between these effects, between triggering and disruption, helps determine how galaxies evolve over time. The pillars of creation also provide a window into the earliest stages of planetary system formation. The disks surrounding the protostars Webb detected are protoplanetary disks, the environments where planets will eventually form. By studying these disks in our galaxy, in regions like the Eagle Nebula, where we can observe them in great detail, we learn about the initial conditions for planet formation. Our own solar system formed this way, 4.6 billion years ago, in a molecular cloud not unlike the Eagle Nebula. The Sun was once a protostar, surrounded by a disk of gas and dust from which the planets coalesced. The Earth, Mars, Jupiter, and all the other planets and moons grew from microscopic dust grains that stuck together, merged, and gradually accumulated into the worlds we know today. The chemistry of protoplanetary disks determines what kinds of planets can form. In the inner regions of disks, close to the forming star, where temperatures are high, only materials that can survive high temperatures, like rock and metal, persist. This is why the inner solar system has rocky planets: Mercury, Venus, Earth, and Mars. Farther out, beyond the snow line, where temperatures drop below the freezing point of water, ice can exist. This is why the outer solar system has gas giants with icy moons, and why the Kuiper Belt is full of icy bodies. The disks around the protostars in the pillars might have similar structures, with inner rocky regions and outer icy regions. Over time, these disks will evolve, their dust clumping into larger bodies, their gas gradually dispersing or being accreted onto the star. Within 10 to 100 million years, planetary systems will emerge, diverse in their configurations, but all sharing a common origin in these protostellar disks. Some of these planetary systems might be similar to ours, with rocky inner planets and gas giants farther out. Others might be very different, with hot Jupiters, gas giants in very close orbits, or super-Earths, rocky planets more massive than Earth, or systems of ice giants, or configurations we haven't imagined. The diversity of exoplanet systems we've discovered in recent decades suggests that planetary system architecture is highly variable, determined by the details of the disk's initial conditions and evolution. The pillars also teach us about feedback, the ways in which stars, once formed, influence their environment and the subsequent star formation. Positive feedback accelerates star formation. A forming star's jet compresses nearby gas, triggering collapse and the formation of additional stars. A supernova shockwave sweeps through a molecular cloud, compressing it and triggering widespread star formation. These positive feedback processes can lead to bursts of rapid star formation, creating large clusters or associations of stars. Negative feedback suppresses star formation. Stellar winds and radiation heat and disperse molecular clouds, removing the raw material for forming stars. Photoevaporation, as we see in the pillars, limits the masses of forming stars by removing their natal clouds before they can accumulate more mass. Supernova can disrupt and disperse clouds entirely, ending star formation. These negative feedback processes regulate star formation, preventing it from proceeding too rapidly and exhausting a galaxy's gas supply. The balance between positive and negative feedback is crucial for understanding galaxy evolution. If positive feedback dominated, star formation would be explosive, rapidly converting gas into stars and leaving little material for future generations. If negative feedback dominated, star formation would be suppressed, leading to galaxies with large gas reservoirs but few stars. The observed universe shows a balance, with star formation proceeding at moderate rates over billions of years, suggesting that positive and negative feedback roughly balance each other. The metals produced in stars, distributed by supernova and stellar winds, gradually enrich the interstellar medium. The first stars, forming from the primordial gas produced in the Big Bang, contained only hydrogen and helium. When those stars died, they released the first metals into the universe: carbon, oxygen, nitrogen, and heavier elements forged in their cores or created in supernova explosions. Subsequent generations of stars formed from progressively more metal-rich gas, changing the chemistry of the universe over time. This chemical enrichment affects star and planet formation. Metals help gas clouds cool, making them collapse more easily. Dust grains, made of metals, shield cloud interiors from radiation and provide surfaces for molecule formation. And planets need metals. Rocky planets like Earth are made primarily of iron, silicon, oxygen, and other metals. Without the enrichment from earlier stellar generations, such planets couldn't exist. The pillars of creation, forming now from gas enriched by earlier stars, will someday contribute their own processed material to future generations. The stars being born there will live for billions of years, for the low-mass stars, or just millions of years, for any intermediate mass stars, and when they die, they'll return their material to the interstellar medium, further enriched with the products of their own nuclear fusion. This cycle connects all stars across time. The matter in your body, the atoms that make up your cells, were once inside stars. They were forged in stellar cores, distributed by supernova, incorporated into the molecular cloud from which the sun and solar system formed, gathered into the Earth, and eventually organized into living tissue. You are, quite literally, made of stardust, atoms whose histories stretch back billions of years through multiple cycles of stellar birth and death. The pillars of creation are one chapter in this ongoing story, a snapshot of the process by which matter cycles through the universe, from diffuse gas to dense molecular clouds, to stars to enriched gas and back again. Each cycle adds complexity, increasing the metal content, diversifying the chemistry, creating the conditions necessary for planets and life. In studying the pillars, we're studying our own origins. The processes we observe there, star formation in a dense molecular cloud, are the same processes that gave rise to the Sun and Solar System 4.6 billion years ago. By understanding how stars form, we understand how we came to be. By observing the birth of stellar systems, we glimpse the past, seeing environments that might have been similar to the one where our own world formed. Legacy and future. The pillars of creation have become more than just an astronomical object. They're a cultural icon, a symbol of the beauty and grandeur of the universe, a testament to human capability to see and understand our cosmic environment. The journey from Hubble's first image in 1995 to James Webb's revelation in 2002 is not just a technological progression, but a story of how our understanding deepens over time, how new tools reveal new truths, and how the most familiar objects can surprise us when we look at them in new ways. Hubble's 1995 image sparked something profound in public consciousness. It demonstrated that science and art are not opposing disciplines, but complementary ways of understanding and experiencing the world. The image was scientifically valuable, revealing structures and processes that advanced our understanding of star formation. But it was also beautiful, aesthetically moving in a way that transcended its scientific content. People who knew nothing about astronomy, who couldn't explain what the pillars were or how they formed, were moved by the image. It spoke to something fundamental in human nature, our capacity for wonder. This intersection of science and aesthetics, of knowledge and beauty, is part of what makes space exploration and astronomy so powerful. We're not just gathering data, we're expanding human experience, showing our species sights that no human has ever seen, revealing vistas that exist far beyond our planet, but that are nonetheless part of our cosmic heritage. The Pillars of Creation image, in its various incarnations, has appeared in countless contexts. It's been featured in planetarium shows and museum exhibitions, inspiring visitors with the scale and grandeur of the cosmos. It's appeared in documentaries and educational programs, helping explain star formation to audiences around the world. It's been reproduced in art, music, and literature, inspiring creators across different media. And it's simply been a presence in popular culture, an image that many people have seen even if they don't know its name or its significance. James Webb's new images continue this legacy while adding new dimensions. They've reignited public interest in this region, showing that even familiar objects can reveal new secrets when observed with better tools. The comparison between Hubble's and Webb's views has become an educational tool in itself, demonstrating the importance of observing at different wavelengths and showing how technology advances our understanding. For the scientific community, the pillars remain an active area of research. The data from Webb's observations will be analyzed for years, with new papers extracting new insights from the images and spectra. Detailed studies of individual protostars, comprehensive surveys of the entire population, modeling of the photoevaporation process, comparisons with other star-forming regions. Each line of research adds to our understanding. Future observations are already planned or under consideration. Additional observations with Webb might monitor the region over time, looking for variability in the protostars or changes in the structures themselves. Observations with other telescopes, spanning wavelengths from X-rays to radio, will provide complementary data. Ground-based observatories, with advances in adaptive optics that correct for atmospheric distortion, can achieve resolutions rivaling space telescopes for some observations, providing additional perspectives. One particularly exciting possibility is three-dimensional mapping of the region. By combining observations at different wavelengths and using techniques like spectroscopic parallax and proper motion studies, astronomers can build a three-dimensional model of the pillars, understanding not just what we see projected on the sky, but how the structures extend in depth. this would reveal which protostars are in front and which are behind, how the pillars are oriented relative to our line of sight, and whether structures that appear close together are actually physically associated or just chance alignments. NASA has already created a three-dimensional visualization of the pillars using combined Hubble and Webb data, an animated fly-through that lets viewers explore the structures from different angles. This visualization, released in June 2024, combines visible light data from Hubble with infrared data from Webb to create a three-dimensional model. It's not just eye candy, though it is stunning visually. It's a scientific tool that helps researchers and the public understand the three-dimensional geometry of these complex structures. The visualization highlights several specific features, including an embedded infant protostar at the top of the central pillar, visible in infrared as a bright red glow, a diagonal jet of material from a newborn star near the top of the left pillar, and a bright, newly emerged star at the end of one of the left pillar's finger-like projections. By flying through the scene, viewers can see how these features are distributed in 3 dimensions, not just on the flat plane of a single image. The pillars of creation have also inspired discussions about the nature of astronomical imaging. Are these images real? What does real even mean in this context? The colors in both Hubble's and Webb's images are false colors, assigned to different wavelengths during processing. The human eye wouldn't see the pillars this way. Yet the data is real, recorded by instruments measuring actual photons that traveled from the pillars across 6,500 light-years of space. The choice of colors highlights different physical processes and makes structures more visible, serving both scientific and aesthetic purposes. This question of authenticity in astronomical imaging reflects broader questions about the relationship between scientific observation and human perception. Science extends our senses, allowing us to see wavelengths we can't see naturally, hear sounds beyond our hearing range, detect forces we can't feel. In doing so, it reveals a universe far richer and more complex than our unaided senses could ever discover. The images we create from scientific data are translations, rendering invisible phenomena into visible forms we can understand and appreciate. For future generations, the pillars of creation will likely remain an important object of study and a touchstone for scientific inspiration. As new instruments come online, in space and on the ground, they'll likely turn their gaze toward this familiar region, each adding their own perspective to our evolving understanding. Ground-based extremely large telescopes, like the extremely large telescope under construction in Chile with its 39-meter primary mirror, will have unprecedented resolution for optical and near-infrared observations. Future space telescopes, potential successors to James Webb optimized for even longer wavelengths or other parts of the spectrum, will reveal aspects we haven't yet imagined. But beyond the science, the pillars of creation serve a broader purpose. They remind us of our place in the universe. We are not separate from the cosmos, but part of it. The atoms in our bodies were forged in stars. The process of star formation we see in the pillars is the same process that gave rise to the Sun and Earth. The cycle of stellar birth, life, and death connects us across time and space to the largest structures and processes in the universe. When we look at the pillars of creation, we're looking at a process that's been ongoing for billions of years, that will continue for billions more. We're seeing the universe create new stars, new worlds, new possibilities. And in that creation, we glimpse the mechanism by which the universe becomes more complex, more structured, more capable of giving rise to phenomena like planets, life, intelligence, and consciousness. This perspective, this cosmic view that places humanity within the broader context of universal evolution, is perhaps the deepest gift that images like the pillars of creation offer. They're not just beautiful pictures or interesting science. They're invitations to wonder, to contemplate our origins and our destiny, to feel connected to something larger than ourselves. As technology continues to advance, as our instruments become more powerful and our understanding deeper, the pillars of creation will remain a beacon, a place to return to observe again with fresh eyes and new tools. Each generation will see them differently, will learn new things, will be inspired in new ways. And through it all, the pillars themselves, 6,500 light-years away, will continue their slow evolution, unaware of the attention they receive, simply being what they are. Columns of gas and dust, sculpted by stellar radiation, cradling new stars in their cosmic arms, living monuments to the creative power of the universe. And now, as our journey through the pillars of creation draws to a close, let the images settle in your mind. The dark, towering columns Hubble showed us, mysterious and imposing. The glowing, transparent structures Webb revealed, warm and alive with forming stars. Two perspectives on the same cosmic landscape, each beautiful, each informative, each incomplete without the other. We've traveled from visible light to infrared, from the surface of the pillars to their hidden cores, from the technology of our telescopes to the physics of star formation, from individual protostars to the broader cycle of matter through the cosmos. We've seen how observation and understanding evolve together, how new tools reveal new truths, how the familiar can become strange and wonderful when viewed in a different light. The universe is vast beyond imagining, ancient beyond comprehension, and yet we are part of it. We are made of its matter, governed by its laws, shaped by its history. When we study the stars, we study ourselves. When we seek to understand the cosmos, we seek to understand our own origins and nature. The pillars of creation stand as a reminder of all this, a symbol of the creative power of nature, the beauty of the cosmos, and the capacity of human minds to see, understand, and appreciate the wonders that surround us. If these quiet explorations through science and wonder have helped you drift toward rest, or simply given you something beautiful to contemplate, consider liking and subscribing. It helps others find their way here too. One curious mind, one sleepy soul, one wonder-filled moment at a time. May you dream of cosmic clouds and newborn stars, of pillars rising through the darkness, of light revealing what was hidden. Sleep well, and know that out there, in the vast expanse of space, creation continues its ancient work, building new worlds under patient, timeless skies. Good night.